Alright, hello. Hopefully everything's working and you can actually hear me. I've had to pretty much set everything up from scratch here in the past little bit because I forgot I reinstalled Windows since last time I streamed, so uh, hopefully I haven't forgotten anything too important here. Okay. Let's see. Cool. Alright. So hopefully now you can see my desktop. Cool. Alright. I think we're good. Alright, so the plan for today is I've been doing some characterizations of the new colorcode.net DFT algorithm that's based on the NC method. So I figured out a couple of the properties of the algorithm that I wanted to understand. And then there's pretty much two more things I want to get figured out, and then I'm going to actually implement the algorithm in colorcode.net itself. So all these simulations I'm doing in Matlab, so I don't know, it just feels like the right place to be doing mathematical simulations like this. It's pretty convenient. So previously I tested the location of a bin. So because the NC algorithm actually uses 2 bins to calculate the value of one frequency, I wanted to make sure that that's working correctly and that I get a reasonably symmetric response around that. And my result pretty much was that if I put the 2 bins equally spaced apart and put the actual target frequency directly in the middle, then I get exactly the result I'm looking for, and it performs very well and is very symmetric. So that was the first test here. The second test I did was checking how the current legacy color code algorithm and the new NC algorithm, how those compare in the bin response width. So looking at a single bin and seeing how strongly it responds to a frequency sweep, and seeing like when does it start responding and when does it stop responding during that sweep. And what I figured out based off that is that NC performs better across the entire spectrum of window sizes. So with both algorithms, as window size increases, the output becomes cleaner, the peak becomes more defined, and there's less noise. And that's true for both, but the NC algorithm both starts in a already more narrow place and gets narrower faster than the legacy algorithm. And on top of that, obviously, the whole point of it is that there's no noise in other bins that are not related to the actual tone at hand, which is kind of the whole reason that I'm implementing NC. So my next experiment here that I'm planning on doing today is checking how that then also relates to sample rate. Now, intuition kind of tells me that scaling the sample rate should pretty much do the same thing as scaling the window size, but I just want to double check and make sure that it behaves as I expect. And then the last thing that I plan to do in simulations is I need to come up with a approximation of how, essentially an approximation for a function that takes in the current sample rate and the number of bins, and then it returns exactly the most optimum window size to use to get the correct amount of overlap between bins. So one of the things I'm planning to implement in this new algorithm is in colorcode.net, it's going to change the window size to best match your other properties, such as your sample rate, so that you have the best performance possible. Okay, that was a lot of words. Lots of Matlab to do today. I should go ahead and get that started while I'm waiting here. Let's get that going. Get this out of here. Alright, and I'm gonna have to we go. Cool. Fantastic. Oh, how do I... Hang on. How do I get rid of this ugly line? Preferences, editor. No, none of that. There we go. Okay, cool. So I'm just gonna write stuff in here because I like this editor better. The Matlab one's a little weird. And then it should auto sync over anyways. Okay. Can everyone hear me okay? Is everything working alright? Just want to make sure before I get too deep into everything that like audio levels are okay and things are working. Oh. Hey, thanks for following. I recognize that name. Can hear you. Sweet. Okay. Let's go ahead. Excellent. Feel free to toss any questions or anything my way. I know I just talked a whole lot, so maybe that didn't all quite make sense. So this one, I'm just to start off with, I just have selected a few common sample rates that I think make sense. I'm just gonna sweep over those, and then maybe later I'll do a more fine-grained sweep of a bunch of different ones, but just to test, I think this is sufficient. Just gonna be messing with TCC. Hey! Are you almost done with the RISC-V stuff? Or do you think you're almost done with the RISC-V stuff, rather? This. Use this as a reference because I'm going to be implementing something reasonably similar to this. And yes. I'm trying to think, do I want to sweep both sample rates as well as window sizes, or do I want to just use a fixed window size? I found more bugs for some reason. Some of the functions called. Oh boy, fun, fun, fun. I didn't expect that that would be so difficult. Probably wouldn't be as difficult if TCC wasn't written like TCC is written, though. Sweeping window sizes. I don't know if that's data I need. I feel like it's pretty much gonna be predictable. So I'm gonna start without sweeping window sizes and just do a single fixed window size. I guess 2048 is fine. And just sweep sample rates. See how that goes. It's also partially due to the fact that you have no clue what I'm doing. Hey, perfect. I have no clue what I'm doing here either. Distinguish between, yeah, true. You lose a lot of the context that you build up. All right. Cool. I guess the only thing I really care about is NC, so I'm not even going to bother implementing the standard algorithm here. Yeah, okay. So let's do this. Center, plot range. I guess I need the plot range. Let's turn that down a bit, 100 for now. Center plot range, okay, so that's our frequency sweep. Yep, looks good. And then sweep, cross frequencies, input the sine wave, do the product, get the magnitudes. Okay, I can pretty much wholesale copy this. Don't care about the random noise, so I'm just gonna toss that out. Also don't care about the standard algorithm, NC only. And I guess I also don't need this. Don't care about that. Peak. Yeah, this is the harder part of this. So let me quickly illustrate what I'm trying to do here. If I run this one, yeah. There we go. So here you can see in blue is the legacy color chord algorithm, and in red here is the NC algorithm. So the big advantage of NC obviously is that it does not respond at all outside of its frequency range, versus the legacy color chord algorithm responds at least a little bit pretty much everywhere. However, I need to figure out a way to calculate this point right here where the NC algorithm stops responding. And I assume that Matlab has a nice function built in to find where that happens, but I'm not sure what to look for. It wouldn't be a minimum because this whole thing is a minimum, so I don't think you can just look for minimums. If I try to do like a, what's it called? What's the iterative algorithm that you use to find like a local minimum? Is it Newton's method? I forgot. Whichever one that is, I feel like that's probably also not going to work, because if it gets out here and it sees, oh, I'm at 0, it's like, okay, it's right here, but that's not the result I want. I want exactly this result here. So I don't know if you know, Sam, if there's an easy way to figure out where something starts being 0. Assuming I know this center point and I input that, I just need to figure out at what point does the function hit 0. I guess I could just, do a for loop, but I feel like there's a nicer way to do that. I guess I can just search. Okay, what's the problem? I'm trying to figure out if there's a nice built-in Matlab way to get this point right here. So assuming I have this input function and I know where this peak is, I want to descend and find the point where it becomes 0. But I don't want to risk it overshooting and giving me something out here, because this is also 0, but that's not what I want. I want exactly this first 0 here. I'm worried if I do something like a find local minimum, it might just give me any point out here. Do you know that there's only peak? Or only one peak? Assume that there is, yes. And that I can tell you the center of the peak and which direction to go. Find indices and values of non-zero elements. Yeah, I need the opposite of find then. Is there a find for zeros instead of non-zeros? See also. Oh, no, not non-zeros. Find 0. Do you want the index or just the data? Well, the data would just be a 0. That would not be useful. So I'm gonna need the index, I think. Nailed it. I can type. Oh, F0? What's F0? Root of nonlinear function. Changes sign. I don't think that's what I want because it never goes negative. I don't think that's what I need. Oh, you can just give it a thing you're looking for. Oh, I missed that. I guess you can also do this, but that does it on everything. That seems less efficient. This seems like the way to go. Oh wait, no, that's doing the same thing, isn't it? That's literally just doing this. It's checking the whole array and then it's finding the first place where this is true. This sucks. Okay, well, I guess it works. I'd probably search the data to find values less than a small threshold and grab the first non-zero value from the Boolean array. Yeah, I mean, yeah, that's pretty much what this is doing. I know for sure that all of the ones that don't respond are actually 0, not some small number. So this should work just fine. Okay, well, that's not quite the solution I was hoping for, but I guess it will do. Okay, so we want to find where... Okay, yeah, I guess fair enough. I was just hoping to have a way that didn't essentially search the whole array, because, I mean, if you look at this peak, I don't know, 80% of the array is not necessary to search, but oh well, whatever. It's probably, I've probably spent more time worrying about that than it's gonna take to actually calculate in all the times I'm gonna run it, so you know what, it's fine. Okay, NC magnitudes is what I'm looking through. So NC is 0. Find the first one. Now what does this text do? It's first. Oh, closed it. Classic. How often do I do the task? What about like 50 times ever? Direction. Oh, okay. Yes. First is what I want then. Cool. Okay, so find where the first 0 is, and this is gonna give me the index, I think, right? Okay. Oh no, it returns a vector containing the indices. Okay, since I'm only gonna get one, I assume it's just gonna give me a single number, so 0 index. I should do that. That's excellent. Excellent idea. Okay. Cut off frequency index. Frequency. So this was just finding the. This was my janky way of finding things that are vaguely like 0. And yeah, that just kind of sucks. Could have replaced all that with just the cutoff and done like less than instead of equals here. Oh well. You live and you learn. Okay, 0 index. So that is for this sample rate. Then I'm gonna want to have 0 points. You know what? I'm just gonna call it peak widths. Yeah, zeros. We want 1 by the number of sample rates. I think. What is that? Len. Sample rates. And then let's see. Peak widths. Yeah, I'll leave it half because this essentially gives me half of the peak width because it's looking only in one direction. So I'll make myself a note. Matlab's comment syntax is bizarre and not the same as any other language I've ever used. To do this isn't actually peak widths at I don't have an index. Okay, damn it. I have no clue why they didn't go with... Yeah. Oh, Fortran. Interesting. I don't think I've ever written any Fortran. I guess, yeah, I don't know how long Matlab's been around, but yeah, maybe that's the reason. Who knows? Okay, I want here SR index. Oh, what did I just do? Equals 1 through sample rates. Wait. 1 through length of sample rates. Do I want a +1 on that? I think I want a +1 on that. Okay. Hooray for 1 indexing. Solves some problems, causes others. In the end, net 0. Okay, and then peak widths at SR index is gonna be this 0 index. Cool. Okay, so theoretically that's pretty much all I need. And we're gonna do plots and figure. Just copy paste, this can be pretty similar. Fortran counter start with exclamation mark. Oh, interesting. Well, I guess it's not from that then. What could it be from? What language does % sign comments? Also, hello, Tingo. Not sure who you are, but welcome. Maybe fireman? Okay. So we're plotting sample rates, and y is gonna be okay. Ingo. Sample rates, and I guess just peak widths. Nice and simple. Run red line, upper 0. Just the one line's fine. Okay, X limits are let's just do sample rates 1 to, what's the syntax for last? Is it caret 1? Thinking of C# here. Oh, it's end, isn't it? Wait, is it end? End is object index. Yes, it is end. This, maybe? Yeah, it's been a while. That looks right. Maybe. Oh. Huh. Also never used that. I hope to never need to use that. Okay, I think I'm right here. We'll get an error if I'm wrong. It's fine. Y limits, I don't want to define, I'll let it auto scale. Title, bin peak width versus sample rate. Next label is sample rate in hertz. This is beak. What is a beak? Peak response width in, or no, it's not. Yeah, okay, I'll call it width, whatever. Unit. No, it's units. It's got hertz. And then this, I just comment that whole thing out. All right, let's see what this does. Alright, cool. Oh, line 9. That early, huh? Zeros. Unrecognized length. Oh, okay. I guess len is not right. Oh, it's the whole word, is it? Okay. I think I have another one. Yeah. Line 11. Oh. Uh-oh. Line 12. Oh, I guess I don't want the +1 then. Alright, that's... not quite there. Why is this getting output? I do not want this in there. Oh. That'll do it. Okay. Why is it 0? Or not 0, but 1 rather. Okay. Let's clear this because I have all the garbage from the other thing I ran. There we go, much better. Peak widths. Okay, that is very much not at all what I'm looking for. Let's have a look and see what was our last NC magnitudes. Okay, so this should have given me 57. Oh, it's starting at the beginning of the ray, isn't it? Okay, I'm gonna have to start. Yeah, because find, it's like, oh, first thing 0. That was easy. But I want it to actually start scanning at the beginning, like at the peak, so halfway through the array. So I guess what I want to do is I want to do NC magnitudes of length NC magnitudes divided by 2. Is that right? I think so. Through to the end. Let's see what that does. Oh, okay. That's... Not sure about that one, Chief. Two, 3, 3, 4, 4, 7. What's... Okay. Let's do some better resolution here. There we go. That's a bit nicer. Okay. Yeah, this is not hertz yet. I'm gonna have to... Oh. All I want to do is click it. I'm gonna have to scale this still, but integer operands are required for colon operator when used as index. Integer operands. Oh, because I'm just dividing by 2. I guess I want to do floor of length. There we go. Now it's happy with me. Okay, let's have a look and make sure that we're getting the right thing here. So NC magnitudes. So it should have started at 500 because it's got 1,000. Well, it's got 1,001, so it should start at 500.5, so 500. And so it's 56 above that. Peak widths 57. Yeah, that makes sense because it probably searched the first one and treated that as index 1. So yeah, I think we're getting the right data. Cool. All right, and then now I want to do peak widths. So we don't want just 0 index, we want, let's see, so our frequencies are equally spaced. So let's do frequency step size. And then I should be able to say that 0 index times 2 times frequency step size. So that should actually get me the width of the peak in hertz, assuming it's symmetric, which for any reasonable number of like window size and everything, it seems to be pretty damn symmetrical. So I think if I do it now, there we go. That's a bit nicer. So it, hang on. So at higher sample rates, oh no, that makes sense. At higher sample rates for the same window size, that means that I'm getting fewer full waves, which means that the algorithm can't work as well because it has less data relatively. So the peak is getting wider. Okay. Now, what if I scaled the window size to essentially have the same amount of time of signal? So a window size of 2048 at 8 kilohertz is a certain amount of time. What if I increase the window size when I increase the sample rate so I have the same amount of time of signal? Let's try that. So we'll do this scales the windows. Keeping a constant time period of input signal. That's what I'm really curious about. Does increasing the sample rate do anything at all? Or is it a flat line now? Okay, so we want, I guess, pretty much window size divided by 8,000 times the current sample rate. So window size divided by sample rates 1 times, damn it, I'll rename this base window size. Sample rates of 1 times the current sample rate. I think that's what I want. Let's see what happens. Oh. Wait, what? $135. Wait, what? Line 35. Oh, window size is no longer an integer. I see. Yep, that's... Nope, don't want that. Let's do ceiling. Oh. No ceiling? What? Is it just seal? Oh, it's just seal. Why is floor and okay. Fine. Yeah, it is. Oh, interesting. Okay. So... Huh. Weird. So, changing the sample rate does not help at all. You can have as many samples as you want of the same waveform, the same length of waveform. You can increase the sample rate as much as you want, and the algorithm is not going to do any better. Interesting. That's not what I was expecting. Does that make sense? You're just getting closer spaced bins. Closer spaced bins? This is looking at only a single bin. But I guess if you increase the sample rate... It lets you have closer spaced bins. Well, yeah, okay, in an FFT, sure. But that doesn't really affect this, because you can space the bins however you want. Unless I'm misunderstanding what you mean. Okay. I'm honestly just surprised that it's like perfectly flat. There's like no noise here at all. Let me try something. Let's fiddle with this for a bit. Okay, let's make this figure 2. Let's say figure 1. And then we're going to hold on. Hold on tight. Say hold off to here. And for each one of these, we're going to plot NC magnitudes. Yes, NC magnitudes. We're gonna say plot or no. I want X first. So X is frequencies, which is input frequencies. That's the one. And NC magnitudes. Yeah, I think that's it. And then, yeah. Yeah, that's it, I guess. I'm just gonna let everything else do its thing. Figure 1, figure 2. Okay. Maybe I should have set some X limits. I can zoom though, right? There we go. Oh wow, yeah, no, that's like, that is perfect. That's crazy. It's the exact same one on it. Granted, I don't have that many points here. So, sure, there might be a very slight variation just in rounding and stuff, but, huh. That's cool. The amplitude is different, but I guess that makes sense because of the higher sample rate. You're essentially just summing more points together, so you're gonna get more. So yeah, increasing the sample rate for this algorithm, if I'm not mistaken, increasing the sample rate gives you no benefit at all. In fact, it just increases the amount of processing you have to do for nothing. So, it's worse if anything. That's not what I was expecting. That's interesting. I guess then again though, technically speaking, as long as the signal is below the Nyquist limit of your sample rate, increasing the sample rate, you technically don't get any more information, do you? Yeah. I believe that's generally the case for DFTs. Interesting. I guess I'm just surprised that it's, even with lower sample rates, it's able to extract all of the information. But, I don't know. I think that's just me not understanding this stuff well enough. Okay, well, let's clean this up a bit and call this one finished. Honestly, I guess I can just leave it like this. Let's increase the plot point count. Let's make this like 5,000. Make the base window size 1024. Because 1024 samples at 8,000 is huge already. Yeah, it's still a reasonable runtime. I should also set some X limits on the. Oh, I forgot to click zoom. Set some X limits on this. I don't have to sit here and do this. Oh, that's pretty. Oh, I like that. That's so nice. That's cool. That is very cool. Alright, that's fine, that's fine. Save all that. Cool. So, if I guess I don't need to, never mind. So, figure one, hold on. I guess I can even just do after hold off here. And then xlim is going to be, let's see, peak widths. So 0 index. Oh, I don't save the 0 index. I guess it's still around though. It doesn't get lost. I can reuse it. So let's see. We want to start off in the middle. So this, let's just do, oh wait, hold up, what am I doing? Let's have the index. I don't want an index here, I want the actual number, don't I? So I don't want to use the magnitudes like, I just want to use bin center. Oh, that's a whole lot easier, isn't it? So I guess I'll do bin center minus 0 index times 1 point. Let's do 2 to keep everything integers. Do that, and then in center plus 0 index times 2. I think that will get me something reasonable. Not quite. It's better, but that's still way too wide. Why is that so wide? Oh, because I'm dealing with indexes, and this one's hertz. Of course. Literally just said that. So 0 index. I guess maybe peak width is actually correct then, isn't it? So I'll do peak widths and times 2. I don't need the times 2 because it's inherently already kind of doubled by being a width instead of a half width. It's not a radius in this case. There we go. That's about what I wanted. Bit of extra space to really show that there's 0 everywhere. And then nice curves in the middle. Cool. Alright, slap some labels on this, give it a title, and call it a day on that. So excellent. Title, label. Is there an easy way to do a legend for this? Not really, I don't think. Sam, do you know if there's a nice way to... actually, never mind. I can do that. That's fine. Yeah. I have the array, so I can just pull the legend out of that. That's fine. Okay, X label is response strength in no units, and X label is that's gonna be frequency, hertz. Bin peak width tests. Yes. Let's say across sample rates. And then legend. I assume I can just give this an array instead of individual arguments, but we'll see. Can you append strings to an array and have it, like, element-wise append? Let's just start by doing this and see if it works at all. Grid on. Okay, I think that's good. I'll call this the summary plot. Is it gonna like that? No. Legend, invalid argument. Okay. I'm gonna assign a set of labels. Yeah, so like each one of these lines corresponds to a sample rate, and I already have that sample rate in a vector. So I just want to have a legend that's like yellow is 9,600 hertz, red is whatever. You need a cell array of the labels. Cell array. I don't know if I've ever done this. Oh, interesting. Huh. Yeah, I don't think I've ever used this. Interesting. Combinations of text do not reduce. So it's like a... It's a matrix where each element contains different data types if it wants, I guess. Okay, cool. Now how do I turn an existing vector into individual elements? Do I just do cell on it like that, I guess? Size vector. Oh, that's a size vector I don't want. Create cell array. Because I assume what you mean is I need to have each of my numbers be an actual cell instead of having them all smashed into one. Because that doesn't really do anything useful. Clone size. I want more than size. I want to clone the contents. Convert. Okay, here we go. How do you have your labels currently stored? It's a vector of numbers. Ideally, I'd love to append a string to every single one of those, but that's not strictly necessary. Convert array to cell array, whose cells contain sub. Oh, maybe not. Yeah, maybe not. Num to cell. As printf in a for loop to generate my levels. I guess that could work. I'm sorry, what? Magic? What is this? What? Magic? Magic square? What is it? What? I've never heard of a magic square. What? Okay, I'm getting sidetracked. That's neat, but not at all what I'm looking for. Okay, I think this is what I want. Num to cell. Okay, let's try that. Okay, so you're saying my legend has to be a cell array, so I should just be able to do num to cell on sample rates. No. Element 1 is not a string scalar or character array. Oh, they must all be string scalars. Ugh. So even though I've now made it a cell array because it contains numbers still, it still doesn't like that. Come on. You can turn numbers to text, can't you? I guess I should probably do what you said and make it a num to stir. Numbers to character array. Yep, I think that's it. And then do I have to then turn that into a cell array? It didn't complain, and it was happy with... Oh, it was not happy with it. Okay, I might... Maybe I just have to, maybe I just have to have it in the other direction. So maybe I just gotta do what... Like... Is that not the right thing? How do you rotate? Isn't it top? Transpose on the vectors. Yeah, that's what I'm doing. I'm just blanking on the right way to do that. Actually, I don't know if I use that anywhere in here. I realize I've just opened the same file twice. I don't actually use it anywhere. Is it that? This is basic stuff here. Yeah, it is. Okay, I'm just doubting myself for no good reason. Oh, there we go. Okay. Honestly, that's good enough. Like, yeah, I would like an HZ after each one, but I don't know. This is fine. So, yeah, I mean, as frequency, or sorry, as sample rate increases, magnitude increases. That makes sense because there's more sample, so a sum of more things is more. Sure. But in effect, the net result is going to be 0 because everything else is going to get larger too. So yeah. Sample rate does not help at all. Cool. Okay, well, I have figured out what I wanted to figure out. So I think this is done. Cool. Next is going to be next is gonna be just figuring out let me run this one. It's gonna take a minute. Oh wait, wrong one. Not location, I want width. This one's gonna take a minute. These defaults are pretty high res. Cool, wait for that. In the meantime, I'm just gonna go ahead and get started. So, let's see. What's the word I'm looking for? I guess it's a regression, maybe? Let me double check that. Regression. Yes. Yep, no, that's the right word. So let's say window, no, not window, yeah, window size. Regression. Okay, and then I'll keep this one. All right, how's this doing? Not done yet. So. Determines a function to get the optimal window size given the, I guess the sample rate doesn't matter, so we don't need to provide that, but we do need to give it the bin spacing, and we need to give it, what else do I need to give it? I guess desired overlap is not gonna be a variable, so I'll leave that as a constant. Huh. Now that I think about it. This is never going to change, is it? I guess it... Yeah, no, the user can configure a different number of bins, so therefore the bin spacing will change. So no, I do need this function. Given the bin spacing. I guess that's all then. Cool. Just go back to a reasonable sample rate. I guess given the bin spacing, I guess I don't really want the bin spacing, but the bin count would probably be easier to integrate. So I'll say 24 bins per octave for now. Bins per octave. Octave is going octate. Octave. Octave is gonna be from 440 to 880. Okay, how's this doing? Still not done? Server's working hard. That's not what I meant. Okay. So I need to come up with a function that essentially does what I've done in here, figures out, like comes up with a good approximation for that curve. And then I can use that curve to find the best window size given the amount of bins. Because if I have the amount of bins, then I know how wide each bin needs to be to get good overlap. And if I know how wide each bin needs to be, then I can just look at the curve and find what that window size is. Okay, it's finally done. So this is what you've probably already seen in the chat before. This is the traditional color code algorithm. This is the new algorithm. And this shows how much that bin responds. So there's only one bin at 440 here in the middle. How much that bin responds to a frequency sweep from bottom to top. And then how that changes as the window size changes. And this is the raw data here. I also did one where I then essentially just like grabbed the shape of this outline here, and that's what we see here. So here you can see in red is the traditional algorithm, blue is the new NC algorithm. You can see that across the entire span of window sizes, the NC algorithm does better, i.e. gets a narrower bin. And it's also a bit more stable down in the very low window sizes down here, where the old one just kind of falls apart pretty quick. So essentially, I need a way to turn this blue line into a mathematical function. Now it looks... I don't know, what does that shape look like? That could be exponential, maybe? It could be like a higher order root? I don't know. Are there built-in tools in Matlab to essentially just like give it a curve and have it tell you, this curve is, you know, an exponential with these factors? I assume it would have something like that. There are curve fitting tools, but they're sort of a pain. Curve fitting. I guess that's probably a better search term. Fit curve or surface to data. Having used them a couple times. Well, unless you can think of a better way to do that, that's not just like brute force me trying numbers until it looks right. That's probably what I'm gonna have to do here. I hope I have the curve fitting toolbox installed, because otherwise we're gonna have some problems here. It looks like some kind of 1 over x. Does it? I guess it could be a 1 over x. Yeah, is there a good way to even figure out like what class of curve it is? Not even come up with the factors, but just be like, this is a 1 over x type curve, or this is a, you know, square root, or this is a, you know, e to the something. Is there a good way to do that? We're now well outside of anything I've ever done. I would export 1/2 of the data as an Excel spreadsheet and then use the... That's a choice. Okay. I feel like Matlab has failed. If the right way to do something in Matlab is to do it, copy out the data, and then do the check in Excel. Yeah, it looks like you have to specify like what kind of curve it should even try to fit. Huh. Okay. Matlab, determine, what would you call that? Determine family of curve? Excel's curve fit tools are just a little nicer to try stuff with. Okay. Plotting a family of curves. Fit family of curves. Determine a curve. That's a nice vague description. Mean curve. No. Each has exponential. Okay, I don't know that. Plotting a family functions. Determine. Determine what family of what family? Let's just try that. Determinant. No, I feel like I might be using the wrong terminology here. If you don't know what the function is, Matlab's okay. If you don't, it's a pain. That's surprising. I feel like they would have implemented something to help you with that. I mean, if Excel can do it, then I don't see why Matlab can't. No, I don't want the mean. Okay, let's just try something a bit different. Be a bit more specific. Determine if curve is exponential or something else. Polyfit. But that's just gonna get me... I think there's some GUI too, but I've not had great luck with it. Okay. Yeah, I'm gonna keep searching for a little bit in case I find something, but... otherwise, yeah, I guess Excel it is. Compare candidate models. That sounds like what I want. Parametric fitting. Least squares. Polynomial, exponential, Fourier series, Gaussian. Interactive. Okay. Compare fits. Ooh. Yeah, I'll see what that one's about. Let's see what compare fits is. Oh, wow. This is... Huh. Curve fitter. Let's see if I even have this installed before I get too deep into this. Because if I don't have it installed, then oh, wait. It's not immediately throwing me an error. Okay. It's taking its sweet time, but I think we're okay. Cool. Load census, as you do. Alright. Open the curve fitter. And yeah, I guess you can just like try them and see what looks good. Huh. Okay. Yeah, I'm gonna try this. If this doesn't end up working, I'll do Excel, but this looks promising. Although, you did say you have not had great luck with it, so my expectations are tempered. Okay, contains two new variables. So your X and your Y, okay? Yeah, that is sort of like the Excel one. I don't know if I tried this the last time I needed to do this. Okay, well, hey, let's try it out. Select data, select the variable names. Okay, so is it gonna just have the workspace data already here? Yes, sweet. All right, I don't need to export and import. Fit name. So I guess I don't actually really need to write much of anything in here. I thought this was gonna be like a code-based thing to do, but yeah, if I'm just gonna do it in the GUI, then I guess this is not gonna happen. Hey, Isaac, how's it going? We are about to be doing some curve fitting. Fun, fun. Working on a new DFT algorithm for colorcord.net, and I'm characterizing different properties of it. And then progress so far is actually going really well, so I think I'll actually be able to start a actual like C# implementation of the algorithm here today, which is pretty exciting. I've been roaring to do that for a while now. Okay. I guess honestly I don't really need to write anything. I can just grab the data off this line that I already have here. So let's see where that's coming from. That is plot number 1, or figure 1 rather. Okay, so lower 0, upper 0. Okay, and then I want upper 0 2. Alright, I'm gonna, let's see, upper or lower, does it really matter? They are different shapes, interestingly enough. We need to grab the magnitude of the envelope. Yeah, instead of trying to do like one of these curves, just actually grab the width between the lines. Yeah, I think that's a... Although, if it's not, like down here it gets pretty asymmetric, so if it's like on a peak like this, then that's gonna be kind of misleading because it's not in the right place. So maybe I should instead average the distance from 440 of both of these. I feel like that might give me something more correct, maybe? Although granted, I really don't want to be down here anyways. I'm probably gonna limit the auto window sizer to never go down into this unstable region, but you know, still probably good practice to do it this way. Okay, I'm gonna write this in a different script to do this nicely then. Okay, let's do, yep, that's the one we want. So, we want to grab the data that is in upper 0, 2. I'll have to look through the final implementation when it's done. I'm curious how it works. Yeah. I'm gonna try and make it as understandable as possible while still being nice and optimized. I'm also gonna try, I've been meaning to try this. I've never done intrinsics in C#, so taking advantage of like vector instructions in the CPU. So I'm gonna try doing that as well to hopefully make it even faster. Okay, upper 0, 2. Yes, SIMD, thank you. That's the word that I couldn't think of at the moment. Okay, NC magnitudes is that, and upper 0 is this. Okay. So this is like my janky ass scanning thing. AVX 512. I think, yeah, if your platform has AVX 512 capability, I think it should just automatically use it then. That's the nice thing about this being a JITted program, is it can adapt to the target at runtime and do whatever is most optimum. You don't have to hard code it for specific possibilities. Okay. So, input frequencies, magnitudes. Yeah, I guess I'm pretty much gonna have to calculate everything regardless, aren't I? This script is kind of slow. I want to make it faster. I guess I could stop the frequency sweep once NC gets to 0, because once it gets to 0, it never comes back up. So I could probably save a good amount of work doing that. Yes it does. They introduced that a couple years back. And I haven't used it yet. And I've been wanting to play with it. Square root of NC mag. Yeah, I guess I can just say I can do the frequency sweep. I don't even need to start at like 0. I can start at the bin. Frequency sweep up until I hit a 0. Reset back to the middle. Frequency sweep down until I hit a 0. Average the 2 places where that happens. I guess not average the 2, that's useless. Find the distance between the center and where it goes to 0, absolute distance, average those 2, and then use that. I think that should get me something that's a decent bit faster than what I'm doing right now. Okay. Bin center, max window size, I need that. No, I'm not gonna put in that effort, whatever. Plot point count, 0 cutoff. I don't need a 0 cutoff because our 0 cutoff is 0. Okay, I'll try. Just put that down there for now. Okay, window sizes. Yep, T. Yep, sine, cosine. Don't need that. Plot range, input frequencies. Do need that. All magnitudes, don't care. Upper 0, lower 0, don't need to store that. Random input, don't care. Okay, for each window size, NC offset, NC magnitudes. Don't care about regular magnitudes. Actually, I also don't even need to store this, do I? Okay. Do the frequency sweep. Alright. Now this is gonna actually be different. So let's do end. So sweep up from center until we hit the first 0. And then we want to do the same thing in the other direction. So sweep down from center until we hit the first 0. Okay, I hate that inconsistency. Let's do upper 0 and then lower 0. And then after we have our 2 0 points, find the response width at this window size, which is going to be okay, I'll do that after because I don't actually know what units this can be in. So for how do you do a 3-part for loop in Matlab? I've only ever used like the concise versions of the where's should have just... Oh, I definitely hit a wrong key there. Why are we... Oh, no. Why are we in... What? We're in English. What? Why is the IME on now? Okay. I guess that's somewhat the remote connection. For loop? Wait, is my caps lock backwards now too? No, okay. That was weird. 4. Index is values. No, I don't want this. I want like a C style for loop. Step by increments. No, I don't want this either. Oh, is there no like... Because I want to start... Ah! Actually, no, maybe I can just use this style. I don't think Matlab has it. Oh, really? Damn, okay. I think I can get away with that style though, because I want to start at frequency index. Let's do frequency index. Where is this coming from? Oh no, that's okay. So the center index, center freq index is going to be plot point count divided by 2. Let's make sure that's an integer. Okay, so we want to start at center freq index. We want to increment by 1s, and we want to go until we hit, well, theoretically until we hit plot point count plus 1, but we're gonna break out of the loop early. Okay, yeah, this will work. And then this is gonna be the same, except our step is going to be -1. Alright. Yeah, I think this will work. And then I assume I can just break out of the loop with break, like I would expect. Yes. Yep, that's exactly what I expect. Alright, cool. Center frequency index. Okay. So we're at the 440 hertz. We're gonna keep stepping up. And we're gonna calculate the magnitude, and if the magnitude is 0, we're gonna set upper 0 and break out of the loop. Alright. So the frequency is this. The input sine wave is this. Oh wait, I forgot to actually set a variable. I assume I can just do index this. Right. Okay. Frequencies. Input sine wave. Okay. I want NC. I actually. No, I do need the actual square root, don't I? Magnitude. No, I don't. I just need to see if it's 0 or not. Yeah, so I don't need to do the square root. Save a bit more time there. NC products. Yep. And then max of 0 or negative NC mag. So NC mag is mostly negative, so essentially I want to see when it goes positive. If this NC mag is positive, we stop the loop. I think. If NC mag is greater than or equal to 0, right? Then we want to break. And we want to also say upper 0 is equal to... Now, do I want the actual frequency in hertz? I think I do. Yeah, that's more useful. Alright, I think that's it. So I should be able to pretty much copy paste this. Oh, copy paste this. -1 there. Lower 0. And I think that's all I need. Okay, find the response width at this window size. So these are both in hertz. So let's say upper 0 minus bin center. So that is the space between the peak and the end of the response in hertz plus I guess bin center minus lower 0. Yeah, that's the space there. Divide all that by 2. That should give me the average. Oh wait, divide by 2, is that one? Add that. So if I do that, I add those two, then I divide by 2, that's a half width. I guess I don't actually want it halved. Okay. Call this response width. Okay. So that is essentially what I've gotten here is the distance between this top blue line and the bottom blue line. For this whole thing. So essentially I should get a graph that starts pretty high and then tapers down towards a low number but never gets to 0, obviously. So yeah, let's save the response widths. Just grab one of these. Response widths is 1 max window size. Response widths at the index, which is, damn it. I never have the index when I need the index. Okay, so we're gonna do size is equal. Or I guess I don't want to assume that this is always one start though. So right now, yes, it is technically an index, but I don't want to rely on that starting at 1 in the future. So window size is at window size index, and then window size index is 1 through length of window sizes. I think that's what I need. And then this at window size index is going to be that. So theoretically, I should be able to just plot this now. So don't need any of that. Window sizes, yep. And then we want response widths. Sure. Don't need a second line. X limit is going to be 1 to max window size. Y limit is going to be plot range. Is that reasonable? Yes, I think that's fine, although I probably don't even need to define it and just let auto scale. You know what? No, I want to make sure it starts at 0. X-line, bin center, title, bin peak, width, test, bin response, width, curve. X label is window size and samples, yep. And then this is bin response width in hertz. Don't need a legend, there's only one line. Let's see what it does. That's a hell of a lot faster. Okay. And yeah, okay. I was gonna compare it, but I guess it closed it. Okay. That does not look right. Because this should be going down towards 0, not down towards 440. I feel like I'm doing something wrong. Response width is... Okay. Let's just... let me... clean up. Oh. What? What? That was weird. Where was that second graph coming from just now? Shouldn't have even been there. Doesn't even have the data for that. That was weird. Okay, so that's not right. Let's have a look at response widths. I assume that's gonna be... Yeah, that goes down to 440-ish, almost. That should not be happening. Upper 0 minus bin center minus lower 0. Okay, I'm gonna put a breakpoint here. Conditional breakpoint. And I want to check when, let's say, window size end is equal to 500, somewhere reasonable. Okay. So upper 0, 489. So 489 minus 440 plus 440. Oh, that's not good. Okay, so this is our problem. So center frequency index. We're starting at 600 and we're going... Oh, I think I found the problem. We're going from 600, we're going down in steps of -1 to 1200. Yeah, I'm confused what that would even do. That's the frequency, that's the sine wave. Hang on. No, I do need this in here, never mind. Okay, NC mag. I'm curious if that's already just reasonable. I don't think so. Oh, I guess that was it. That was all I needed. I'm not even sure what that was doing then. That was definitely the wrong way around. Okay, well, I think we're good then. Let's see what this graph comes out as. There we go. Yes, that looks reasonable. Okay, so now I have nice clean data. I can just run the curve fitting on this. I am going to increase the resolution of this a bit, because I can see where it's transitioning. So let's do 2,500. Ah, screw it, let's go 3,000. Oh, I'm just gonna get rid of my point. This should just get me a higher precision result. Ah, that's much better. Now I can't see obvious, well, I can kind of see obvious steps, but meh, it's fine. This does not need to be super precise. Okay, so we have that data now in response widths. So let's go to the curve fitter and let's follow the instructions. Introducing curve fitter. Wait. Oh, that's like two different instructions. Which one do I want? Okay, I'm just gonna do compare fits. This one looks more. Okay, I'm gonna move this to a different window so you won't be able to see it, but you'll see what I'm doing. Or different display, not different window. Okay, select data. Fit name. Bin width. Fit. I don't know. Whatever. Okay. Fitting data. Okay. X data is input frequencies, right? No, window size. Window sizes. Okay. And Y data is response widths. Yes. Oh, what's going on there? That's not good. Why is that going negative? Oh, cause yeah, it's like totally trashed in there. I'm going to, real quick, before I do anything, I'm gonna clean that up because I don't want that screwing with my result. So, how do I do this? Is there a good way to say, like, ignore this? I guess I can say last bad index is 0, and then for width index is from 1 to my response width. That should not be in this loop. Why is this in this loop? Or actually, you know what? There's a... No, I do actually want to do this afterwards. Okay, then if response widths at width index is greater than let's say 800, or is that how you do or? Or I guess it's actually just one line. Okay. Or oh, is it? I find logical or okay, I'll just try both, whatever. Okay, if response width is greater than 800, or if response widths at width index is less than or equal to 0. Well, 9 is a bitwise or. Oh, okay. Alright, fair enough. If it is bad data, then we want to set last bad index to be width ind. Okay, and now we know like the range of data that's good. So you know what? Let's just call it good window sizes is window sizes from last bad index plus 1 through to end, and good response widths is the same. And then I'm just gonna double check by plotting this. And then xlim. And xlim is just going to be good window sizes 1 to good window sizes end. Ylim was already fine. I don't think I need to do anything with that. No, that wouldn't change. Okay. Let's try running this again, make sure I've got my head in the right place here. Hey, that looks good. Now we don't have all this garbage, but that's... Oh no, that's the vertical 0. Ugh, that looks so misleading. I don't like that. Yeah, because the 0's... Okay, I think I'm gonna make that start at 0 when I'm plotting regardless, because that... I don't like how misleading that looks. So, 0 to good window sizes. And... honestly... That was fine, now that I think about it. Should have just run the bottom part. Could have saved like 10 seconds. There we go. Yeah, that looks much better. That also makes it a lot clearer that there is bad data off here. Okay, now that shouldn't impact our results. Cool. Plots. Now I can just run the section. Much better. Okay. Cool. Alright. Back to this. Except we're gonna... Good window sizes and good response widths. Okay. Okay, curve fitter creates plots. Yep, the default fit is a linear polynomial fit type. Observe the settings in the fit option. Oh, okay, I guess I just close that now. Alright, the fit is a first degree polynomial, i.e. a line. And the fit options pane, change the fit to a second degree polynomial. Okay, yeah. Okay, cool. So you can fill with it like that. Fig, okay, because auto is selected by default. Okay. Curve fitter displays the results. Fitting the data with quadratic polynomial in the results pane, where you can view the library model, fitted coefficients, and goodness of fit statistics. I'm sure these numbers mean things to people who know you know, statistics, but that's not me. Change the name of the fit. I don't think I'm gonna do that. Display the residuals. Ooh. On the curve fitter tab in visualization. Residuals plot. Oh, that's cool. Okay. We want r squared to be close to 1. Alright, we can do that. And we want this to be like small. Residuals indicate that a better fit might be possible. Therefore, continue exploring. Okay. Add new fits to try the other library equations. Right click in the fit in the table of fits pane. Oh, so you can actually like have multiple to compare them against each other. Okay, cool. Well, let's start by finding some that look good at all. So an exponential was one of my initial guesses. Okay, it's not looking too hot just yet. That's not terrible. Okay, let's add a fit. I should have given this a much better name looking back at it now. So let's do exponential. And then this one, what was the one you wanted? You wanted 1 over x. Is that even an option here? Power? No, it's not power, is it? I guess I do custom equation. Okay, exponential Fourier. No. Gaussian, no. Power. Let's try power. Just to see what it does. Oh, I have to select the data again? Oh. Can I copy this? Oh, I should probably just have duplicated instead of... Yes. Ooh. Okay. 2. That didn't really help much, did it? A times x to the b plus c. Oh, okay, that's just adding a constant though. That's like free. Who cares? Okay, so that's an even better fit, it looks like. Yeah, like overall that is, especially like down here at the super low end, I don't care too much. This can be off in the weeds, that's fine. But really long term, I want this to be as close to 0 as possible. And this is doing a hell of a lot better job of that. Okay, let's see if we can do duplicate. And then we're gonna try rational. What's rational? Fit a rational model. Right. Let's see what it does. P1. Oh, hey, this is what you wanted. This is 1 over x. Okay. That's very similar to power. Can I zoom? I can't tell if that's selected. No, that's not selected. Oh, okay. This is just kind of slow for some reason. Oh, that looks so weird. Oh, you know what that might be? That might be artifacts of the fact that I have like discretized data that snaps to individual values, and this is obviously a smooth curve. Okay. So I feel like if I want to get a better fit than this, I'm gonna have to get higher precision data. But I don't know, I feel like we're already doing pretty good. I mean, a residual, that's like 1. 1 hertz of difference on a 440 hertz peak is probably close enough. Well, yeah, but what I'm saying is like these numbers, because of the artifacts we're seeing due to the precision limitations of my data, these numbers are kind of bogus. I should just get higher precision data. You know what? Let's make the server work. Let's do it. There's probably a much better way to do this, that instead of like checking discrete points, I could do like some kind of like what's it called? Like Newton iteration or something, to get a much more non-discretized point where it is 0, but I think we're getting into the weeds if I try and do that. This shouldn't take too long. So yeah, I mean, I guess really in the end, this is pretty much what you were asking me to do in Excel, except this is probably even a bit nicer because you can like directly compare different things and have nice plots easily. Okay, data looks good. How do I now refresh this? Update auto. Didn't find this last time. Oh, okay. Maybe I just gotta do this again. No. Oh, there we go. Okay. I guess I just have to manually do it. Alright. The R-square is the same? Did that not change? 99264. I don't know if that actually did anything. Maybe that had already refreshed. Okay, I guess whatever. We're gonna rename you to rational. The R-square is being dominated by the low window sizes. Yeah, that's fair. Which, yeah, I guess that is something I should also actually be a bit more careful about. I don't want to completely ignore this. I do want to see... Okay, these are like almost identical. There's so little difference between these that it's pretty much not worth. Although this one, hang on. Okay, so this one definitely, it doesn't quite fit. Versus this one, like on the higher window sizes, like that's pretty bang on. And then as you get into the lower window sizes, it gets a bit offset. But this one, it's kind of offset everywhere. It's not really great anywhere except this small region here. This one is just kind of garbage everywhere. I don't think it's an exponential function. Yeah, that tells me that's not right at all. So yeah, maybe the rational... So hey, I think you were right. It is something over x plus something. Good guess. Well done. Coefficients. Q1, so it's essentially 50,000 over X plus 11 and a half. Huh. Those numbers mean essentially nothing? As far as I can tell, that's essentially meaningless. Okay. So we're gonna grab these coefficients, and I'm just gonna plot that on top of the original data, and then just do a... Ideally, they would mean something. Yeah, ideally, but... I don't know. I mean, sample rate is 48,000, but that... Also, sample rate doesn't matter. Never mind. Ideally, yes. But... Yeah, no, it wouldn't actually depend on any of these numbers. Yeah. Yeah, no, I don't think there's anything I can compare these numbers to in my program. Yeah, okay. Alright, and then let's do... So, what is the y-axis? It is bin response magnitudes. Or sorry, no. The y-axis is bin response width. Width. This is width. So it is the distance between the... No, I don't have anything open. It's the in that earlier plot where you saw the two blue lines diverging. It's the distance between the top line and the bottom line in hertz. No, I said I wasn't gonna do that, didn't I? It's the Q of the bin. Is it? DFTQ. Is the Q defined as the full width, or is it only half of the width? Because, like, you have like a curve, right? Is Q the distance between the peak of the response and the end? Or is it end to end? Usually full bandwidth. Okay, so in this case, yeah, I guess then that might be Q as it stands. Oh, Jesus. I made the mistake of looking on Wikipedia for the discrete Fourier transform, and suddenly I don't understand anything anymore. Oh no. There's probably some relation to the number of samples and pi or something like that. Number of samples. I mean, that's just window size. And then pi. Yeah, I guess. But... I don't know, man. This is too abstract for me to be able to think about. Okay. Cool. Plot of actual data. And then we're gonna do... so this is the... curve fitting result. So we've got our window sizes and that. Anyway, the physical interpretation of the curve fit has something to do with the relationship of Q to the window size. Yes, I mean, the curve fit is literally the relationship of Q to the window size. So I would hope that the curve fit has something to do with the curve, right? Okay. So f of x. So that f of x in this case is Q of... Okay, let me write this down. F of x means the Q of this window size. Right? Yes. Okay. And then... So I'm going to do... I guess I literally can just... Could probably define the values as some sort of DFT figure of merit. If you want to be both hand wavy and technically accurate. Sure. Yeah, if you want to do that, go nuts. Right. Can I get some more precision on these numbers? Because like 11.48 isn't exactly... Oh, I just realized also, we can fiddle with these degrees. I never even did that. Wait, what? Did it zoom me out? Yeah, it did. Okay, so if we go back. Yeah, why does it reset the zoom? That's so misleading. I thought it was suddenly so much better. Come on. Don't be like this. Denominator degree. Oh. I think I Wait, what? I think I just completely broke it. Oh, did not converge. Well, there we go. Okay, so maybe... I assume it's only... Oh! Nope, that's... Nope, that's complete garbage. Okay, so it's definitely degree 1 on the denominator. Let's just go all the way up and see if it does anything. Oh, okay. Never mind. You know, I think we're gonna stick with what we have. What? I think I might have broken it. These are the settings I had earlier, and now it's giving me garbage. What? Good. No good response. It's rational. I shouldn't have screwed with it. I should have just left it. It was good. Now it's garbage. I didn't do anything to this, so... Okay, what we're gonna do, we're just gonna redo what we did earlier. Oh, that looked interesting. Rational. Okay, okay. I probably like auto changed some of the advanced options when I fiddled with it, and now it couldn't properly do it anymore. So we're just gonna pretend that that didn't happen. You saw nothing. I didn't do anything. Okay. All I wanted was to know if I could get higher precision numbers out of here. So let's see. Coefficients. Start point. I guess not. Try exporting it. Oh, you're right. Export. Literally right there. Oh, generate. Oh. Here I was writing code. But like, oh, okay, that's a lot. But I can simplify this. Function, create fit. Oh, this is like, oh, so this actually does do the calculation of the fit. Okay. Well, I don't really want to recalculate it. I just want the... Yeah, but like it actually redoes the fit instead of just giving me the actual function for the fit. Okay, let's see. Currently selected fit. No, I just want the... Try exporting the data to workspace. Okay. Save fit. Save fit output. I think that's what I want. Save goodness of fit. I don't care about that. I'm gonna not do that. We're just gonna try output. Output. 1 by 1 struct. That contains... Oh. Maybe not. Yeah, this is not what I wanted. Fitted model. Hey, that's... Damn it. See fit. This is like some special object. Yep, it's a curve fit object. I want this number, but better. Let's see if I just... Oh, I can't fiddle with that. Okay, can I save as? And we're just gonna try... Yes, matlab.mat. Perfect, thank you. But anyway... Oh, that's binary data. Can I remember there was an ASCII way to do this. Maybe? Oh, the variables that... Okay, I can't... Mat files are HDF5 encoded. I've never heard of that. No, don't just... Okay. You can get the data out of it. Coefficients. Okay, yeah. Let me just try that. Matlab get coefficients out of CFit. Returns the values of the coefficients. Okay, so I guess I need coef values of fitted model. I'm confused. Oh, derp. Okay. It's just showing us in a bizarre way. But that is what I want. Yes, okay. So now, if I just do this, save as, Sure, we're just gonna keep using this shitty name. Oh, I did it again, didn't I? Save as M. There! Okay, we got him. Alright. So this is our numerator coefficient, and then we have our denominator coefficient. Alright. Nice, precise numbers. Not that I need this much precision, but hey, I'm not gonna complain. Okay, and then we can delete all this garbage. So matlab.m. Yeet. Yes. And then did the .mat just go away on its own, I guess? Okay, works for me. Alright, so we can close that. We don't need any of this, I don't think. Nope. And then, okay. So, this was done by using the, what is it? The curve fitter tool to find an that needs a bx plus c. Uh-oh. No, it's just x is single. It puts... Yeah, there's no multiplier on x, so I guess it's not a denominator. I guess it's still a denominator coefficient, but it's more like a denominator offset or something. I don't know. But yeah, x is alone. I guess it just integrates that into the other two. Yeah. So yeah, let me just make that very clear here. The function is, although I'm literally about to write it out. Actually, what's the syntax to make a literal function out of this? Because that'll be even clearer. Okay, so it's function. Let's see. Curve fingers. So what is this? Bin width at window size, not same word. Bin width at window size is equal to okay, I'm confused. That's syntax. Am I looking at the wrong page? Declare the function named myFun accepts. Wait, what? Oh, this is the inputs, right? I always forget that this is so weird and backwards. Okay. So, wait, is it? Calculate average that accepts an input vector. Calculate. Return name. Okay, yeah, it is backwards. Okay. So this is width. Bin width at Windows size of Windows size. Make this small because argument. Bin width at Windows size, and then it's going to be width is equal to, and it was the 50,000 over x plus the other one. Okay, so it's not even a coefficient, it's just straight up the numerator then, isn't it? Numerator over window size plus, I'm just gonna call this size offset then. And honestly, I think it's even clearer if I just don't give these names because they don't mean anything anyways. Alright. I think that's the right way to do that. Cool. And then we're just gonna make another nice little plot. So I will just sweep across all window sizes. I don't need to do any special things here. And then just do fitted bin widths is equal to bin width at on window sizes. Can I do that? I assume I can do that. And it's just gonna do this for each one. Yep, okay. And then just plot. Actually, you know what? I'll just toss them onto the same figure. Hold on. Fitted bin widths. And then we'll just do window sizes. Wait, you need a dot divide. Ah, good catch. Do I also... Dot plus... No, I don't think so, right? Because it's adding a constant. That could never do anything that I don't want it to do. That could never not do what I want it to do, rather. Okay, window sizes, fitted bin widths, and then make this one blue, I guess. Plot, don't need to change that. X label, Y label, grid on, and then we'll do legend. So this is the actual bin response, and then the approximated bin response, fitted bin response, calculated. No. Modeled? Modeled. I like modeled. And then hold off. Okay. Start run to end, I think. Oh. Must appear at the end of the file. Okay. I forgot Matlab has like really weird restrictions on this stuff. Okay, plot actual data to the bottom. Okay, run to end. There we go. You know what? I think that's pretty good. I think that's solid. Yeah, it doesn't look pretty down here, but I probably won't be using much lower than like... I'll probably cap it even at like 256. Yeah, that puts it like right there. And everything above that is pretty damn close. Okay, cool. 256 is already ridiculous. I don't know if I'm ever gonna need a bin that is anywhere near that large. Like, what would you even need? You would need to make it like 2 or 3 bins per octave to get that low. Yeah, no. So pretty much everything's gonna be down in this area, which looks really nice. Cool. All right. did that. Say this. I guess then this isn't really. Yeah, let's just say. Put this up here. I should actually instead do this. Do that. Good night. I've got uni tomorrow. Alright, thanks for stopping by. Have a good night. There we go. Alright. Plot of actual data and modeled function. Cool. Alright. And then I need to wrap this function in another function that then uses it and actually takes in like a bin per octave and gives you out a window size. So for that, I'm gonna need to figure out like what kind of overlap I want. And this is the part that I really was unsure of going into this. So the NC response is like a really nice hump that has very steep sides. So what do I call good overlap versus too much overlap versus not enough overlap? Try finding 3D. The other big problem is because the window size is constant and the spacing changes across the whole octave because it's an exponential series. If there's too little overlap on one end, there's probably going to be too much overlap on the other end. So we're going to have to try and find a good balance for the midpoint there. I obviously don't want to have individual window sizes for each bin. Or do I? Is that okay? Is that going to be too hard to do? Yeah. That's what I was going to suggest. Really? The problem with that idea, though, is then wouldn't I have to... How would I actually implement that? Does that throw out some of the optimizations that I can do between octaves? I guess maybe not, but the window size is gonna have to snap to something that is 2 to the power of octave count. Because otherwise the resampling is just gonna be completely trashed. That's interesting. So as you... Oh, that's weird. I don't know if I like that. So as you increase the number of octaves, the like achievable bin overlap quality goes down because it has to snap to larger and larger values, or larger and larger increments. Huh. And granted, you know, a decent normal-ish value of, I don't know, let's say 7 octaves. That's gonna give me 128. So window size is gonna have to snap to multiples of 128. Which is kind of coarse, but probably not too bad as long as, you know, you have like 12 or 24 bins per octave anyways, so it's probably fine. Maybe. On the other hand, I could divide the octave into 2. Instead of dividing it into n bins, and instead of having the whole octave be one window size, I could split it into like 2 or 4 and do them independently. I guess really the answer here is I gotta actually plot something and look at it graphically and then figure out, you know, how bad is it? Do I actually need a different window size for every bin? So let's do that. Do I still want to do that in this file? I guess I can just keep going in here. Yeah, why not? Okay. Plot of actual data on mounted function. Alright, so here we're going to find the window size that best fits the number of bins. But before we do that, we need to plot bin overlaps across an entire octave. Although, I might want to make this one actually depend on the data I do here. I think that'll make this easier. Yeah, okay. Stepping out to do some cooking. Alright. See you in a bit. Okay, so I'm gonna start by optimizing at the middle of the octave, because that way I think the middle is the right place to do it. I don't know, because it's an exponential series, so maybe the middle is not the right place. With dynamic window sizes, it would be possible to have wider bins where notes are more hertz apart. Yes, that's the whole point. So, my dilemma right now is, to what extent do I do that? If I have one window size for the entire octave, then I'm gonna have bins on one end that are like not overlapping at all potentially, and bins on the other end that are overlapping way too much. However, if I have every single bin have its own window size, then I can make them all perfect, but that's a lot more computationally involved when the algorithm's actually running. So, my goal right now is to figure out, like, what can I get away with? Can I get away with just 2 window sizes per octave instead of having every bin have its own window size? Or can I get away with 4 window sizes per octave? Or would it really be best to have every bin have its own window size? That's kind of the goal of why would it be more involved? Because each bin wouldn't... As you go between octaves, the audio is resampled. So it starts on the highest octave and it resamples the audio to be 2 to 1, essentially speeding up the audio to double the speed, and then reuses the exact same calculations with the exact same bins again. But that resampling, if every bin has its own window size, that means that every bin is going to need to have its own resampling done, I think. unless I pull out, unless I only store the data once in a single largest window, resample it down. Yeah, I could avoid resampling it for each one, but if I do that, then window sizes have to snap to 2 to the power of octave number of samples. Reducing window size is just dropping data. The thing is, you have to be consistent. So when you resample at the beginning, when data comes in, you need to have exactly the same result when you're doing that as when you then resample the end and when the data is getting pulled back out, because otherwise you're going to have error accumulate over time. So the resampling needs to happen on exactly the same data, and if the window size is wonky, it might not grab the exact same, n samples of data to resample. This is really hard to explain. I'm probably not making much sense, sorry. Resampling is only for octaves, right? Yes. Yes. So within an octave, all the 24 bins in this octave, there's no resampling that happens. The top octave operates directly on the raw input audio data. Then, to do the next octave down, we resample the audio to be 2x speed, which is really just you take pairs of samples and average them. And then you just do the same 24 bins on that resampled data. And then you take that resampled data, you resample it again to speed it up 2 times again. And that's how you get your third lower octave, etc., etc. So if you have 7 octaves, by the time you get to the bottom octave, each sample is actually 128 samples, 2 to the 7, 128 samples of the original audio data, all averaged together. And when you add the data to that lowest octave, to those accumulators, you need to make sure that then on the other end, when the data is old, because it's a big finite response filter, or finite impulse response filter, so it's essentially a big shift register for that data, the resampled data. And so when you then take the data out of the other end, you have to make sure that you're getting the exact same 128 samples averaged together in order to have the same thing go in and out of the filter. Otherwise, you're going to accumulate error over time. And in order to have exactly the same data resampled... Hey, Zenith, welcome. Sorry, we're in the middle of something very complex at the moment. In order to make sure you have those exact same 128 samples averaged, that's only gonna work if the window size to start with is a length that is a multiple of 128. Because otherwise, when you resample down, you end up with like half resample. Like if the window size is, let's say, 253, right? When you resample down one, that last sample, what do you do with it, right? You either put it into the one before or you just discard it. I guess that doesn't necessarily mean that the higher one can't be an quote-unquote odd number, but it would make the code a hell of a lot simpler if it was. Well, maybe not even necessarily that much simpler, but just... I fear that I'm gonna make mistakes if I don't do that. Yeah, for the downsample you want 2 to the n. But that means, because we're downsampling, let's say 7 times for 7 octaves, I guess we're only downsampling 6, sorry, we're only downsample 6 times for 7 octaves, because the top one doesn't get downsampled. So okay, let's pretend we have 8 octaves. We downsample 7 times to the bottom one, which means we have 128 samples in each. For note DFT window, you can reduce the window to make the bin wider. Note DFT window, you can reduce the window to make the bin wider. Yes. But... I guess... Yeah, I guess the higher octaves don't necessarily have to conform to that 128. You just have to throw out a little bit of, like, any trailing data that doesn't fit into a nice multiple when you're downsampling. Is that the only problem? If that's the only problem, then that I can handle that. I thought there was some other specific reason that the window size had to be constant. Maybe it doesn't. This is one of those times where it's like, it would be easier to know what the limitations are if I already had the algorithm implemented and I was just trying to tune it, but I'm starting from scratch here. So I don't yet know all the implementation details of the algorithm and whether attempting to do this will cause problems when implementing it. Okay. Let's start. Okay, let's do this. I'm going to start by just using one window size for all. Yes, the non-uniform bin spread. Yes. That, I mean, that's going to happen regardless. That's very important that we have non-uniform bins, or non-uniform bin spacing. And because we have non-uniform bin spacing, we ideally want non-uniform bin widths so that we always have ideal overlap. I'm going to, just for now, I'm going to start by making all the bin widths the same in an octave and seeing how bad that is for overlap. Because maybe it's like, oh, it's like 10% low on one end and 10% high on the other end. In that case, I don't care. But if it's like, there's no overlap at all on one end and there's way too much overlap on the other end, then I'll look into this again. But I don't know that right now. So let's start by figuring that out. Okay. Jeez. Center note is going to be... Okay, you know what? We're going to build another function here. This function calculates the frequency of a specific bin inside an octave. Mentioned he didn't have a fixed width and he's using a constant QS transform. Okay, yeah, that's what Isaac was kind of... That's what Isaac and Sam both were kind of trying to point me towards, using a different window size for each bin and therefore have a fixed width constant Q. Yes. I'm wondering if I can get away with not doing that, and that's why I'm exploring that right now. Worst case, I will do that. I just fear that there are repercussions in the implementation that I'm not thinking of right now. because the algorithm as it currently stands specifically avoids doing that. And I feel like there's a good reason for it. Maybe I'm wrong. Function. Pretty sure you don't have to do that. Yeah, you can do both ways. Yeah, I mean, it's more ideal for it to be constant width because it makes the overlaps much nicer, but I don't know how much nicer is. Is it a bit nicer? Is it almost required nicer to get good data? I don't know. Because this is kind of a problem in the existing algorithm. There are like almost dead zones, and then there are zones that are overrepresented because of too much overlap. I just use whatever WASAPI gives me as the window. Wait, what? Whatever WASAPI gives you as the window. Like the buffer size? That's not even constant. And it's way too small. What? Like on my system, the buffer size is 440 samples, I think. Which 440 samples would give you complete garbage. That's way too small. I guess I do ask for the smallest possible buffers, though. Maybe you don't ask for the smallest possible buffers. Oh, do you also get 440? Wait, I thought I got 480. I don't remember. And yeah, one thing I also noticed is sometimes the buffer, like sometimes it'll just give me two buffers, a larger one and then a tiny one. Because I guess something's like kind of wonky with the timing or something. I don't know. It's sample rate of system divided by 100. Oh, really? I've definitely seen inconsistent buffer sizes. Yeah, it's not guaranteed. So you're relying on like not necessarily guaranteed numbers here. It's not guaranteed, and I'm pretty sure I have seen it not fulfill that requirement. It's not like a, oh, this might someday change. It's like, I'm pretty sure I've already seen this happen. Yeah, you kind of are. Okay. I mean, hey, that makes life really easy for you then. You don't have to like have a, you don't have to have like a rolling buffer of historical audio data that you then like add and subtract from. You literally just get buffer, deal with buffer, done. Fair enough. Okay, no freak is equal to note freak at. Okay, we're gonna do exactly. I don't think the output looks that bad considered. Yeah, fair enough. If it works, it works, and that's what really matters in the end. Skip this for now. Dark and C#. I'm just gonna real quick look at nope, not OneDrive. Shares, stream development. I shouldn't be able to see that. Okay. It shouldn't even be enumerating that. That's weird. Anyways. Cool. Colorcode.net. Note Finder. Base Note Finder DFT. Do you know what's a Base Note Finder? So simply, yes, this is what I need. Just drag this over here and redo this. Okay, note frequency at. So I need Wait. Okay. I don't need this. I only need 2 to the bin index divided by bins per octave. Okay. So octave start. Then I need bins per octave and bin index. Alright. So frequency is going to be octave start times pow of 2 to the bins per octave. Bin index over bins per octave. I think that's right. Let me test this. We're just gonna do notes in octave is note freak at on 440 bins per octave 24. Bin index is going to be from 1 to 25. Now bin index, I think I actually need to subtract 1 because this is 1 based. 2 to the 0 over that. 2 to the 0. That is times 1. Yeah, that's octave start. Yeah. Okay, good. So 1 through, let's make this better. Bin count plus 1. I think. Let's try running that. Yes, this section to end. Oh, okay. Function definitions. Move all statements after bin with at to before. It is. There's no statements. This is another function. What? It did. Please tell me it's not complaining about that. No way. It actually won't let me have a blank line. Okay. What is POW? Is it just power then? Oh, wait. I just do POW too. Oh. That's even better. Matlab or dark theme at? There isn't one. At least not one that actually is any good. So we're stuck with this. Sorry. Oh, POW. Yes, POW 2. On this. Yep, it's unfortunate. Okay. I'm gonna want to run from this section to end. Yeah, it literally was complaining about the fact that I had a new line in here. Wow, okay. That's... I don't know how to feel about that. This should be done though. I can't. Alright. So, now notes in octave. I should see 440. Let's just cross-check this real quick. Note frequencies. Yes, delicious, high quality image. So we start at 440, 466.16. Yep, looks good. Then 493. Yep, okay. 523. Yep, okay. So this is working as expected, and it should end. Oh, it ends at 880. Okay, I don't actually want that one, so I guess I only want 24. Okay. So 1 through bin count. Oh, don't want to hit the big green button. So now, yep, 440 all the way. Okay, perfect. Cool. So we got that. Okay. Go back. This is why I, well, this among, the syntax highlighting in this is, I mean, it barely exists. And I definitely like to have a bit of highlighting in my code, which is the other reason that I'm using VS Code here. Don't need this anymore. Don't need this either. Alright, octave span. So, are we defining? No, let's do this all separately. So yeah, octave. Octave at 1. Bin count, and we want this to be bin count over 2. VS Code syntax highlights MATLAB files better than MATLAB. Yeah, I guess it does, huh? Maybe there's options you can turn on in here. I honestly haven't fiddled with like the editor settings too much. Yeah, so you can like, yeah, you can play with stuff. I'm sure you can make it look nice, but like out of the box, VS Code is just doing what I want, so meh. Okay, so this should give me the note that's halfway into the octave. Let's check that. Run to end. So notes in octave, yep, so 604. Is that exponentially halfway between 440 and 880? Yes, that sounds right. Cool. So let's do halfway frequency. So I'm gonna put a little comment here. This is the frequency of the note that is in the central bin. That is in the central, that is the central bin, rather. Okay. Does color coord use a logarithmic y-axis? I don't think it does. I think it's linear. At least in the version of the DFT that... Is it linear? It's linear with a few, like, small adjustment. It's mostly linear. It has some non-linearities, but overall it is linear, as far as I know. Yeah, it's normalized. There's like a bottom cutoff as well, and then there's a little bit of scaling that happens, but it's all... It's still linear. There's no, like, it's not logarithmic, it's not exponential, nothing like that. It's linear-ish. Which, I guess that's something else I could consider, is using a non-linear output. I don't know if that would really help with anything, though. I don't know if that's actually something I want, either. Something to consider. Okay, halfway frequency. So, what do we want to do? We want to do the halfway frequency. Let's just say the next frequency. Next frequency is no freak at octave 1 bin count, count, and then we want bin count over 2 plus 1. Note that is the central bin and the one above it. And now it's no longer this, it's just frequencies of the note that is the central bin That English sounds awkward, but whatever. Next frequency. Okay. So we're gonna have these two, and we're gonna find the ideal amount of overlap between these. Now, Sam said I should try and overlap at the -3 dB point. That would require me to figure out where that is on the shape of an NC response curve, which I don't know offhand. So for now, let's just put in something, anything at all. So we want to do bin width at window size. I guess I want the inverse of this, don't I? I want to give it a bin width and it gives me a window size. How do I do the inverse of this? I'm already using that name elsewhere. Let's call it preferred size is equal to window size for width for bin width. Okay, now I need the inverse of a 1 over x plus something, which I solve for this. Is that easy to do? I think so, right? Hang on. Let me double check this on paper. So if I want yeah, it's just that over that. Okay, cool. So we're gonna do the preferred size is going to be this over bin width, and then outside of that this time we do add, no, subtract that. Someone check me on my math there. I think that's right. Subtract that. Yep, I think that's right. Okay. So then we want preferred window size is window size for a bin width of I guess I could start by just the distance between the frequencies. That's probably too big. Let's do distance between the frequencies divided by 2. So next freak minus this freak divided by 2. Okay, I'm curious what that's gonna give me. I got a message. Do right here, and let's see. Okay, it doesn't like this. Oh, I call it. Don't know where I got that from. All right, preferred window size is 5,659. That's a surprisingly reasonable number, given that the current algorithm uses 8,192 and this one needs less window size. 5,659 sounds... Yeah, okay. I like that. Alright, then what we're gonna do... So that is the preferred window size here. And now we're just gonna do the whole octave with that window size and see how it looks. Okay. What's the best way to do this? I'm gonna reuse plot point count. Best fits the number of bins. Okay, plot point count, we're gonna make this back down to like 1,000. Then input frequencies. Oh, do I already have all this? I don't know if I wanna. Okay. This would probably be better to do in a different script, wouldn't it? Yeah, I'm starting to feel like I'm putting too much in this one. Alright, new file, and let's do window size optimization. Alright. Grab all. Actually, yes. Yes, it is. Okay, bin with that is actually used up here, but none of these other things are. Okay. That looks more reasonable for that. Okay. And then I can use same nice. Names, keep things consistent. So sample rate 48K, bin center. What's the general idea for calculating that? There's been a lot that's gone into that. So I essentially took a bin peak width. Is this what I want? Yes, this is gonna run forever. Let me do this one. So here you can see the response of the traditional color code algorithm in blue and the NC algorithm in orange. I swept across different window sizes. This is at one single window size. I swept this across a whole bunch of window sizes to check how this width between like the 440 center and the top and the bottom where it goes to 0. I found a relationship between window size and this width. Then we used the curve fitting tools in order to come up with a mathematical approximation for that relationship between width and window size. And then at runtime, it's actually going to optimize based on the number of bins that you want the algorithm to have. It's going to optimize the window size so that those bins have the best overlap to give the highest quality output. Which is something that is sorely lacking in the old algorithm right now, because right now it's just kind of hard-coded to 8,192 window size, no matter how many bins you have, which isn't super great. So yes, it's all gonna be a lot more dynamic and a lot nicer in the new implementation. Hopefully that made sense. Alright, 1,000. Max window size, don't want that. Bin center, don't want that. Sample rate, okay. Window sizes, don't care. I just want a single window size. T. sample rate. Okay. Yes, I think that's right. Okay, and then we've got our time. I'm gonna need to bring back. Let's bring back. No, let's bring back location. Okay, sample rate, blah, 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 blah. NC offset, NC bin. I have to do this inside a loop now. So we want 4, I guess I should have a nice little thing that's bins is from octave 1. Actually, no. Let's start by just doing 1 through bin count. Bin count? Is bin count what I want? I think bin count's what I want. Then bin frequencies is going to be at note treat at octave 1 bin count. And then bins. And I'm realizing I could have just kind of... It's fine, whatever. Go ahead, good luck with the dev. Thanks for answering my question. Yeah, no worries. Thanks for stopping by. And frequencies. Yes, okay. Then I'm gonna do each one of these independently and just plot them all on the same graph, and it should look fine. It'll be fine. Okay, for bin index is equal to 1 through, no, just bins. Some room to breathe. Then INC offset, NC bin, blah blah blah. I guess I should set bin center to be bin freaks at bin index. Then NC offset, grab all that, toss it in. Plot range, plot point count, input frequencies. I guess I can leave that constant-ish, maybe? Yeah, just to keep it simple for now, I will. Yeah, that's not what I want. So I want to put frequencies in from octave. I was trying to spell octave today and I don't know why. Octave, plot range, plot point count. So this is not going to be plot range, this is going to be octave span over plot point count. And then that goes up to octave end. So this will give me linearly spaced frequencies between 440 to 880 with a number of points that is plot point count. I guess +1 maybe, but who cares? Okay. So then we've got T, sine, NC. I need these. T, yep, that's constant. Magnitudes. Yes, I guess I should do magnitudes. Bin count plot point count. And frequency index. Wholesale copy paste time. Frequency index, that's vague. I don't want to leave it named frequency index. What is the Control F2? I'm so used to using Visual Studio, and there it's Control R, Control RR. I really wish that it was consistent between the two. Okay, frequency index. We're gonna replace that with sweep frequency index, because we have two frequencies that are being swept, or two. Yeah, I guess you could consider the bin sweeping. Two different frequencies we're dealing with. Input frequencies is, yep, input sine wave is that. We don't need any of that because that's the old color chord algorithm. We only care about NC. We don't need to do this either then. Okay, NC magnitudes at sweep frequency index and bin index. Is that okay? I think that will get me what I want. Maybe. There's a chance. Bin center. Bin center. Yeah, no, that looks right. Okay. So now I guess I should actually put it in the section I literally made for that. So we're plotting. Can I give it a whole matrix and will it plot all those as individual lines? Plot multiple sets of coordinates. Oh, yes. Okay, that looks good. So I should be able to literally just say NC magnitudes over input frequencies. Actually, that might just be right. There's a chance. Okay, and we want our xlim to be the octave. X line, don't care. Title, bin, overlap test, frequency, legend, don't need a legend, it's gonna be pretty obvious. Grid on, hold off. So I should technically hold. Do I need hold? I don't think I do. Okay, let's see what this does. Close that. I think we're pretty much done with this as well. Is there a way to... Yes, I can just save session as... Cool. Let's see. NC... width... Yeah, no, it's all NC. Bin width... Curve fit. Okay. And I think we can just close this. Alright, then do a size optimization. Let's see what this does. Oh, damn, okay. Oh, maybe not quite. Something's not looking right here. What is all this garbage? These, the spacings look correct though, so that's a good start. I guess I do in fact actually want the 880 though, because otherwise I can't check overlap at the top end here. But I gotta figure out what the hell's going on down here. This ain't right. This ain't right at all. NC offset is sample rate over window size. Ah, that'll do it. Yeah, if your NC offset isn't perfect, you get complete garbage. And I should have cleared my workspace so I would have actually noticed that. There we go. Look at that. That's kind of pretty. Let me get the 880 in here too, though. Octave. Halfway first. Bin count. I assume I can just do this. And hopefully that just does it. Yep. Easy money. Okay. Yes. This makes the problem very clear. So. Yeah, here they're way closer. Here there's tons of space. However, I don't have any overlap at all. So maybe this divided by 2 was actually not what I needed. And I don't want any dividing here. There we go. So yes, this right now optimizes for these 2 bins to touch. Obviously I want more overlap than just touching at the bottom, but good to see that that's all working, because that looks pretty much perfect. Let's verify. Well, you know what? That's close enough for me. Okay, I would like to, if possible, have these curves shaded to make this a lot easier to read. Matlab, plot, shade, region under curve. Shade area under plot. Patch objects. Okay. Shade area under curve. Area. Shade area under curve. I just want a really simple answer, not any of this complicated stuff. Area. Okay. Well, hold on. Unless I actually don't want the line at all. Do I want the line? Yeah, they have the line. And in fact, they actually draw it after. Which makes sense. Area. Okay. So... oh, I'd literally give it exactly the same. Okay. Let's try that. Nope. The length of X must match the number of rows of Y. Okay, so I guess I can only do one at a time. Alright, let's try one all. Just see if that works as I expect. No. Input frequencies is 1 by 1001. Wait. Oh, derp. I don't. This is already just a vector. There we go. Okay. Yes, that's what I want. So I guess I'm gonna have to just do that in a loop. Okay. Ideally, I would like the colors to match, but I might be asking a lot. Okay. What is it? Clear all? Then 4. Literally just this. Alright. That should theoretically work. Bins. What? Oh, bins? Oh, wait. Clear. Oh, I feel like clear all might not be doing what I think it is. Oopsies. What's the thing to clear the figures then? Oh, yes. Oh, that's pretty. The colors don't match, but you know what? Other than that, it's pretty. Close all. Thank you. Do you know how to make the colors match? Because probably all I need to do is, like, reset whatever index it's using to pick a color from. Because I assume if I reset it to the same, it'll increment and, like, use the same colors throughout the colored pattern, right? So how do I restart that? Plot colors. Specify plot colors. There's a color values. Usually just by making an array with the colors I want and indexing through that. Yeah, I could do that. I was hoping that there was just a super simple way to tell it, like, start over. Reuse the same color palette. Color pal. Yes. Change color scheme. Color map winter, color map. I guess maybe if I just tell it to use the color map and then I just tell it to use the color map again? I guess I could try it. Let's see, color map. Oh, actually, does this even... Is this even what's used in plot, or is this only for, like, surface plots? Surfaces, patches... no, I actually don't want a color map. Color scheme? No. Plot, color scheme. Nope. Okay. Don't look elsewhere. Matlab. Plot lines, color scheme. Specify plot colors. Control how plotting functions select colors. Like automatically assigns different colors. You can customize, and you can also set properties. Add marker. No, I don't want to. How automatic assignment works. Here we go. Assigns colors to plot objects by cycling through the colors listed in the color order property of the axes. Contains an RGB triplet. Contains 7 colors. Oh, okay, so... Sounds like maybe the right way to do this is to actually just do what you were saying. Possible positions for given the colors and simple color order array. Oh, yeah, I could like override the color order array, but... I feel like that's meh. will just... How do I get 24 unique colors, though? I guess I just have to hand pick them. Or at least like a 6 or a, you know, multiple. Color order, okay. Color order, my colors is can I not do decimals? Yes. Oh, sweet. Okay, I just have to do this. And then, okay. So I'll just pick 6 colors, I guess. Let's just do, we're out of music. That's no good. Can't have that. Alright, I'm just gonna pick oh. Nope. And then do 0C0, 0CC, 0C, and then C0C. That should hopefully work. This did nothing. Do I have to do that in here somewhere? Oh, okay, yep. I guess close all. He was unhappy with that. Okay, so I've got my colors now. I guess I have to reset the color order after again. And then let me also make these not quite so ridiculous. Damn it. I can't help but notice that those colors don't match. Oh, because I don't have... I don't have 24, I have 25. But... Theoretically then, if I make it 5, it might work? Yep, alright. I hate it, but... You know what? Fine. What would be really nice is if there was a way to make these partially transparent, and then I could just toss the lines completely. Is that a thing? Is Matlab fancy enough for that? I feel like it's not. Matlab, area plot transparent. I think there's probably a way to do it, but I haven't ever tried. Yeah, okay. That's just a waste of time at this point. Let's move on. Okay, well, here you go. This is what happens when I optimize for these two right here to, like, touch or be, like, directly adjacent. Actually, is it that one or is it this one that I'm optimizing for? I don't remember, but you can clearly see that, you know, it's almost there. This has way too much space, and this is overlapping. Now, obviously, I don't actually want to have it touching. As you said, you recommended the -3 dB point. So I need to figure out how to actually find that. Can you plot this in dB? I guess that might be helpful. Yeah, how do I do that? And then, yeah, I'm gonna need to figure out. Now, the shape of NC curves, I assume, is consistent. So, if I find, like, I'm thinking that the -3 dB point is always going to be X% of the way from the peak to this end. And since we know this distance and we can calculate this, we just need to get some fraction of that distance, and that's our -3 dB point. I don't know that for sure though. So, okay, I'm gonna try plotting it. You'll also probably want to normalize the magnitude to 1. Yes, that I do want to do that. Okay. Let's do that here. So, is there a nice way to do that? Normalize? Normalize. Returns the vector. Oh. Nope. This is like a normal distribution, isn't it? Is there a different normalize? This is frozen. I can't interact with it. Divide by the number of samples. Samples? Wouldn't I want to normalize the amplitude? This is what I want, but this is like Simulink stuff. I don't think I can use this. The amplitude is based on the number of samples. I mean, the amplitude is based on, I mean, whatever it's giving me. I don't think there's a clean... I don't think there's a clean relationship there. Alright. In your DFT algorithm, you could divide by the number of samples. To normalize. Really? Can I do that? What do you mean by number of samples? Like the window size? I feel like this is not gonna do what I want. This is what one random person has said on the internet, therefore it must be correct. Nope, not even close. Got him. I assume that doesn't work on a whole matrix, but only on... I guess... I don't technically know if these are all the exact same height either, do I? That might be normalized area too. Yeah, okay. So I guess I want to do this on each one independently. Okay, that's fine. So I'll do... I'm just... Nope. That's magnitudes at bin index. All of them is equal to that. Let's see it. Hey, we got him. All right, beauty. There you go. 1. Okay, now you wanted decibels, so let's do that too. You wanted NC magnitudes to be equal to 20 times log 10 of NC magnitudes. Oh. Right. This breaks the area. Which is unfortunate. The lines are broken too. I don't know why the lines are broken. Let me just turn off the area for now. Where's the area at? There's the area. Are you doing a stem plot? No, I have an area and just a plain old regular plot. Okay. That really doesn't... Huh. Interesting. I was expecting this to go much further down, but I guess it's just a... It really just falls off, huh? Damn. Okay. Interesting. I guess if I do more of these. Zero is negative infinity, so it doesn't get plotted. Yeah. Yeah. I'm just surprised that, like, it only goes down to minus 20, and then the next sample is already, you know, minus infinity. It's just that clean, huh? That's crazy. Cool. Yeah, I'm gonna set some Y limits on this. Let's do Y lim on, say, negative 30, 0. It's probably fine. Should have just run the section. Keep forgetting to do that. There we go. Overlapping at minus 6 or minus 9 seems about right. Okay, so like the bottom is already getting there. The top is, well, a little too far apart for that. So I guess what we can pretty much deduce from this, without even trying to do any more math, is we can say that, like, Actually, you know what? No. Let's do just a tiny bit more math. And instead do... I'm going to rename this to be reference frequency. Frequencies... the two frequencies... Okay, we're gonna say Bing count -1 Bing count. I think what that should give me then almost. Okay. Something's not quite right with the math. There's some weird offset somewhere. But you know, if these are close to, if these almost have no overlap, then on the other end of the octave we're going to be overlapping at like -2. Is that... That's a bit far apart, isn't it? I would like that to be a tighter range. Yeah. So we're going from literally no overlap to like more than half the power is in overlap. That's a bit steep. However, if I cut it in half and I just do 2 window sizes per octave instead of giving each bin its own window size, we go from like -6 to -infinity-ish. I mean, like I said, this isn't perfect. Which... yeah. Essentially, I would put like the optimum overlap here, and then another optimum overlap here, and then it would just get worse, get better, get worse, get better, get worse, get better, get worse, etc. Is that acceptable? Is 2 good enough? This is 24, which is what I generally want to color code at, and probably what I'm gonna continue to have as the default. Let's try it with 12. Yeah, that's... okay. That doesn't change that much, surprisingly. Is that just... You're probably okay with little to no overlap at that number of bins. You know what I should do on top of this? Let's do this. I have an idea. Before you go anywhere, with that, let's do NC magnitudes. Oh, there's no. My inner Pascal case is screaming, but. Okay, and then what we're going to do is we're going to do NC magnitudes total. We're going to do, how do I do a column-wise sum? Is there a nice way to do that? Because this is a matrix that has 13 by 8001. I want each of these sets of 13 to be added together, so I end up with 1 times 8001. Man, I used to know all this stuff back when I, took a class on Matlab, but I've forgotten it. I've forgotten so much. I guess I want to sum columns, right? Oh, cumulative sum of column or row elements. Oh, that's like, damn it. Cumulative sum. Okay, let's just check, see if this will do it. Oh, wait. Is the column vector containing the sum of each row? I think that's what I want. It's a column vector containing the sum of each row. That sounds right. Okay, let's just try it. Meh, what could go wrong? Wait, what am I doing? Sum of that, comma 2. Okay, can I... oh no, my NC magnitudes is already overridden. I don't want to... Okay, NC magnitudes total is 13 by 1. That's not what I wanted. I wanted the other direction. Damn it! I guess I can do this? Maybe. There we go. Or use one. Oh, can you just do that? Okay, I thought this meant it's like a 2D thing to sum across. Yep, you're right. I'm just dumb. Perfect. Okay. And then I'm gonna want to re-normalize this, because this is something weird now. NC magnitude. Actually, do I? No, actually, let's try not normalizing it. I'm curious to see how that looks. NC magnitudes. Let's just call it sum. NC magnitudes sum dB. Should give me this. And then we're going to plot frequencies NC magnitudes sum dB, and then I'm just gonna say dash K, I think, for black. Let's see it. Ooh, fun. Okay. I want this to no longer end there, but maybe there. Should I just run the section? Oh, that looks wild. I mean, it makes sense, but it still looks really bizarre. Okay. Interesting. So yeah, I would say that this is too much overlap for sure. And something like this is probably ideal, so that it kind of evens out something vaguely like one of these two. So it kind of averages out to about 0 dB-ish. But doesn't, we also, yeah, I definitely don't want this. This is no good. Because then you're gonna be like looking at internotes more, like with more sensitivity than actually looking at notes. And that's undesirable, I think. Maybe even something like this is okay. The question is, can I handle like 6 of these options? Yeah, that's not too bad. Let's try upping the bins again. Actually, let's go 48. Let's see if that actually helps here. Or if it's the same, just more occurrences of the same size peaks. I assume it's just more. Oh, this is kind of cool. Yeah, okay, so more bins doesn't really help. Unless I actually go and like do window size per bin. Then of course it would help, but I guess what this tells you right here, though, is that NC will never be useful for if you care about precision, because you're never going to be able to accomplish a linear response across all frequencies. So don't go using NC for numbers you actually care about. I think it depends what you want. I guess. I don't know. What does the response for this of like a typical FFT look like? I would expect it's a flat line, but maybe it isn't. Probably make it flatter, but if you only care about being very selective with a few well-defined frequencies. Yeah, okay, sure. I meant like, you know, if you're trying to have something that's stable for a Fourier transform and then an inverse Fourier transform, and you want like good stability between those, NC is never gonna work. Okay. Well, I don't know. Is 2 window sizes per octave good enough? That is my question. And I think the answer is probably. However, the idea of window size per bin is attractive. And I kind of want to try implementing that. I guess you might have been gone for this part. Yeah, you were gone for this part earlier, Sam. We were discussing, especially Isaac was saying that it would be best to have a unique window size for each bin to get like the perfect overlap on every single bin. And I was trying to figure out if that would cause difficulties in implementation, like if some of the optimizations could no longer be done. And I think my answer was as long as you maintain the resampling to have like a whole number of samples. Like if you're resampling down from a window size of 333, you cannot resample that down because there's one sample left over, right? So as long as you always throw out that extra sample instead of doing anything else with it, essentially treating that as a window size of 332 then, as long as you do that with each resample and you're careful with adding and removing the exact same data, I don't think it prevents me from doing any of the other optimizations that the color code algorithm offers. But this is one of those cases where I feel like I might not be thinking of something until I actually go to implement it, and then I realize, uh-oh. I don't know. I couldn't think of anything. And so, while 2 window sizes per octave are probably sufficient to get decent quality output, I want to try implementing window size per bin and seeing if I can manage that. But if it makes it any slower, I don't think it's worth it, because we can sit here, we can be like, oh no, it's gonna end up being like 2 dB too sensitive at certain points. But in the end, like 2 dB, it doesn't really matter, does it? This isn't meant to be precise, it's a visualizer. That wasn't really the goal of implementing NC, was to have the absolute perfect response. It was more to have a clean response and not have these endless like extra humps off to the sides. So on that note, I think it's time we hop over into Visual Studio. Now, I did start an implementation of a traditional color code algorithm at some point, but at this point, I think this is just gonna get thrown out, and I'm just gonna restart this all. Because there's, like these tables, I want to do that differently. I'm gonna do this differently, so it's not like the, no, I'm gonna do it very differently. So I think the way to go here is, okay, we can keep octave count, bin per octave, window size, sample rate, bin count, start of top octave, bin okay, everything else I think we're gonna toss. Yep. Yeet. Alright. Oh boy. So this, how do I currently do this in here? Oh, in here. Distance, configure by bias. Doesn't the algo downsample the unmodified buffer? I was thinking to only reduce the window of the DFT as a specific note. Doesn't the algo downsample the unmodified buffer? What do you mean by unmodified buffer? Like, I was thinking to only reduce the window of the DFT of a specific Yeah, not sure what you mean with unmodified buffer, sorry. Oh, I guess octaves isn't even configurable right now, so I don't actually have a octaves. Sure, octaves. Min value 1, max value 50, default value, let's say 7. Where does 7 get me? That gets me from Gets me from 22.5, 1, 2, 3, 4, 5, 6, 7. No, that's not enough. 8. Yeah, let's do 8 octaves. 22.5 by default. Copy, paste, start frequency, all right, static, I guess I should just make everything things. Oh, these are not static. Why are these not? Oh, because I do instantiate this thing. I'm still gonna make everything static, I think. It's getting the idea. Well, it was. Oh, not bad. The config stuff another time. It's not important right now. I have a minimum frequency. I have an octave count. I have bins per octave. Window size is not going to be Do I want to allow the user to override the auto window sizing? Is there ever any reason that they would want to do that? I don't think so, right? Probably not. Separate the incoming IOs, yep, okay. Total number of bins, overall octaves, get the index of the first bin in the top octave. Ah, okay, yeah, sure. Yeah, I think that's good enough. I do need a highest window size though. So max window size. It's not gonna be that, but void. Configure. Calculate attributes? No, not attributes. Calculate. I don't like this name. Okay. So let's grab this, toss it over here. Alright. So one thing we want to do is we also want private static float window size for bin width. Okay. So I'm guessing it starts with a sample rate of 48 kilohertz, but whatever. Then you run the algo to get the spectra for 1 octave. Yes. Then downsample by factor 2. Yes. And if you run the same algo again on the downsampled data, you'll get the spectra of the octave below. Yes, exactly. We resample the audio so that we can reuse the exact same bins. Size for bin width. Nice magic numbers. Woohoo. So you downsample the whole buffer, yes. But you can use a reduced window for bins that you want to have wider. Yes, I'm just gonna have, it's going to be a single, so like the top octave, let's just go with the top octave for now. The top octave is going to be a single buffer that is the size of the largest window size out of all of them, which I assume will be the lowest note in the highest octave, right? Because that one needs to be, yeah, that one's the closest spaced, so it needs to be the least width. Lower width means larger window size. Yes, okay. So the lowest note in the top octave is going to have the largest window size, and that window size is going to determine the size of the audio data buffer. And all the other notes are they're just going to pretend to only see, you know, a fraction of that buffer. Which is gonna get a little janky. But not computationally more complex, just implementation is gonna be more complex. But that's okay. And then when it gets downsampled, if the buffer is an odd number in length, we just drop the last sample, essentially treat it as a rounding error, downsample, now we have either an even or odd number again, and we just treat it the same way as we did before. However, the length of that buffer is now half. Is that wrong? Oh, thanks. Very nice. Maybe later. I guess. Well, that's a whole nother problem, isn't it? Huh. Only downsample once when you move to the next octave. Yes, yeah, there's only going to be one buffer per octave. I'm not doing, 24 buffers per octave. That'd be insane. My next question is, if we start, let's pretend for a second that the top octave has a buffer size of 8,192. We resample, we now have a buffer size of 4,096. Which means that our widths are going to be totally wrong now. Because we're suddenly going to have way more overlap. So does the buffer size remain, like, do we take in twice as much data and keep twice as much history, resample down to be the same number of samples? That would allow us to keep our widths nice, but it adds kind of a weird effect where the lower octaves have more history. If you have 8 octaves, having your super low notes have 8 times more history. Wait, no. Is it 8 times more history? Oh no, it'd be 2 to the 8, wouldn't it? Or 2 to the 7, I guess. I don't know if I like that. That's way too much history. Huh. We're back at that whole dilemma of time resolution or frequency resolution. I guess. Huh. Traditional color chord uses the same for... Does it use the same for all of them? No, I don't think it does. Oh, well, okay, this one just... It doesn't actually keep the history because it just IIRs it and just kind of assumes that that's good enough, doesn't it? Ugh. Yeah. Yeah, it just adds to the bin the current data and then just IIRs it and just kind of goes, good enough. But I specifically don't want to do that. I want to add to the bin, and then end samples later, I want to remove that value from the bin. Sam, do you know if the other DFT modes also do this? Like, are they just an IIR? Are there no proper, like, FIR filter modes? Or is it just this mode that's IIR? Alright. Cool. I look forward to it. I don't know. In the meantime. It's getting late here, so I'm out. Have a good stream. Alright, thank you very much for stopping by. Been pretty helpful in getting me to think about some stuff I hadn't considered, so it's excellent. I'm curious how color chord handles that now. Because is this why the lower octaves are so much more sensitive than the higher ones? Because on the lower octaves, if you're using the same amount of data, because the IIR is the same for each octave, I think. Right, double check that. It's not. Oh. Oh boy. Oh no. I'm not sure how linear this is. That seems questionable. Oh, hey! Captain Noob, how's it going? Thanks for following. Thanks for stopping by. We are working on, so, I did, actually, you know what, I should probably change the stream title at this point. We're no longer doing Matlab. We did a bunch of Matlab. Oh, that's not fun. Yikes. Oof. Yeah. Power outages are pretty rare here. Where I used to live up in Canada, though, it was like 20, 30 times a year. Now here, I haven't had one in well over a year. Anyways, did a bunch of Matlab earlier, came up with some like curve fitting stuff to find the most optimal ways to space bins. Did a bunch more calculations, got cool graphs like this one. Now I've done pretty much all the simulations I need in order to feel like I'm ready to actually implement the new algorithm. So that's where we're at. Let me go ahead and update this. We're now working in C#, and we're no longer characterizing the algorithm. We are implementing it. Implementation. Spelling is hard. Hopefully that updates that. Okay. But right now the dilemma I'm faced with, and I'm struggling to think through. I don't know how familiar you are with the color chord algorithm. I assume not particularly. It's a resampling algorithm where the top octave uses the raw audio data, every octave below that resamples the data. So the octave directly below it resamples the audio data to be essentially twice as fast. It speeds it up by 2x. And then reuses the exact same analysis bins in order to check for those frequencies. And because you sped the audio data up by double, you're essentially now checking for frequencies that are half of what your actual tests are. And you know, because octaves are exponential series which double in frequency, you can just keep repeating that and keep resampling to get every lower octave and reuse exactly the same analysis filters to get those lower notes. However, as you resample down, the way that the resampling is currently handled, which probably not ideal, but good enough, is to just sum pairs of samples. So you take the first sample and the second sample, sum them up, that becomes your new first sample. Take the third and the fourth, sum, that becomes your second sample, etc., etc. The dilemma I'm currently faced with is, when I resample down, do I keep the window size to be the same, i.e. if the top window size has 8,000 samples, do I make the next window size 8,000 samples and therefore have twice as much audio history? Or do I leave the same amount of history but then end up with a window size of only 4,000? Both of which have problems. If I make the window size smaller by not introducing additional history, then all of this like bin spacing optimization and bin width optimization goes completely out the window for the next octave down, because now all of a sudden like the window size is half. All the spacings are totally wrong. On the other hand, if I do this across 8 octaves, by the time we're at the bottom octave, we're storing 128 times as much history as we are for the top octave? Which is also kind of terrible because, I mean, I think that's pretty obvious. I don't want to be storing that much audio data. You're gonna end up with a visualization for what happened 3 seconds ago in the low notes then. Oh, rip. Monitor just went out. What? How does that even happen? Anyways, the current color code algorithm is pretty janky. And uh-oh. That's not good. It shouldn't be smelling like anything. What to do? Okay. Let me get some idea of what I'm looking at here. What is this preferred window size? Okay, so this is a window size of 4,000 samples. At a sample rate of 48,000. I did that backwards. 4,027 divided by 48,000. That's 84-ish milliseconds of audio data. If we try to stretch that through... Oh, wait. This frequency probably has something to do with that, though, doesn't it? If I actually bump this frequency, and I look at the actual octave that this would be, which would be octave 2, 3, 4, 5, 6, 7, 8, 9, okay. 5760. So it's going from 2880 to 5760. What was that about keeping lots of audio samples? Because that resampling doubles with each octave lowering, if we're looking at 8 octaves, by the time we get down to the bottom octave, we're storing 2 to the power of 7 times as many audio samples, which is 128. 128 times as much audio history for the lowest octave as for the highest, which means the visualization on the bass notes is going to be, you know, what happened over the past 3 seconds, versus the top one is what's happening now. I don't know if I like that disconnect, but That's what I'm kind of measuring right now, is how bad is it actually. Window size optimization, let's see. Okay, that's good. So our preferred window size at the top octave is 605. Damn, that is tiny. So 605, sorry, 48,000 divided by 600, divided by 605. Nope, I did that backwards. Wow, I'm getting tired. So that's 12.6 milliseconds of audio for the top octave. And now we do 128 times that. That's 1.6 seconds of audio. It's not about... Yeah, no. It's not about like, oh, that's too much RAM. It's... If we're looking at the past 1.6 seconds of audio, the visualization is not going to line up with what you're hearing, because it's going to be looking at so much history. Eight octaves is a lot. It is kind of a lot. I mean, that gets you from 22.5 hertz all the way up to 5,760 hertz. Which I'd say covers music. We could maybe chop out one of the bottom octaves. Starting at 55 is arguably not too bad. Hmm. That would chop it down to only 0.8 seconds of audio, which... Yeah, I think that's still reasonable. 0.8 is maybe a bit on the high end, but tolerable. That's what I had for my wavelet visualizer. Okay. Hmm. $55 hertz to 5,760 hertz. Going from 12 milliseconds of audio to 800 milliseconds of audio. In reverse order. My other concern with that, however, is if the lows are so slow to respond and so like smoothed out over large windows, that's gonna make beat detection pretty difficult. Cause like, maybe it's okay. I might just have to run like a secondary transform for just like the lowest octave to do beat detection on. Have it have much less history. Yeah. Maybe. That's worth considering. I could just have like one super wide bin that covers everything down there. That wouldn't be particularly expensive. Okay, so that's probably fine. 0.8 seconds. That's still... I don't know, that feels like a lot to me. Is there a way to avoid both problems that I'm not thinking of? A way to have both shorter window sizes and yet keep all of the good bin spacings and widths? I don't think so. Those two are directly related. Is there a way to avoid having either of those cause problems? Lower octaves could... Lower octaves could have some kind of window function applied, where older audio data is considered less important. I don't know what effect that has on bin widths. I feel like that might cause some weird artifacting. Could we do something with bin change velocities? I.e., because the lower bin... I feel like that's going to introduce a lot of problems. I'm going to say it anyways. Instead of using the lower bin data directly, could we... Because the longer window size is going to effectively smooth out changes over time. Like you're applying a giant smudge to it, really. Could I, instead of using that smudged data directly, use like velocities? So if you see that the smudge is starting to get smaller, you not the smudge. If you see that the bin is starting to respond less and less, that implies that the newer data has less of that bin, because it's the older data that's getting removed that's causing it to go down. So could you exaggerate that change to cause it to go down faster? Does that even make sense? Like, effectively do a derivative on the bin magnitude, multiply that derivative by some number, and then integrate that. I feel like I might be going a bit too deep here. That's a low pass filter, no? Wouldn't that be a high pass filter? So let's say our bin responds in a fashion that looks kind of like a sine wave. The differentiator, yes, they integrate low pass. Oh, I guess it's bias. Alright, and then let's just say 10. That's a bit of room here. Times this by 5. Then we get a reasonably decent shape here. Good. And then do this from, what was it, this? 0, x, 10. Alright, let's assume that our, actually, yes. Let's assume that our bin, you know, has response, and then over time the response goes away. I already regret putting all these factors in here. Why don't we just make this easier? Alright. So we have also this no front. Okay. So now if what's the derivative of sine? It's negative cosine, right? No. It's positive cosine. X. Yeah, I got there. Eventually. Shouldn't say. Yeah, I got you. Okay. And if we multiply this by 2, let's say. No, that's not gonna get me anywhere, is it? If I now integrate this, I'm just gonna get the original but double as tall. What was I thinking of then? There's something like 2x? Oh. This is probably more along what I was thinking then. Huh. I feel like this is not gonna work. I mean, maybe it could work, but it's gonna be so much more intensive that I don't think this is the right approach. Okay. So that ain't it. Isn't your data already smoothed out by the binning and resampling anyways? Yes, that's the problem. It's gonna be too smoothed out when it gets to the bottom octave. So I want to somehow be more responsive. Unsmooth it. Because you hold 1.6 seconds of data and you only get your data after that. It's not that you only get it after that, it's that the whole window of the past 1.6 seconds of audio data is being analyzed. And so, what happened like 2 notes ago is just as important to your algorithm as what's happening right now. Assuming you could fit 3 notes into 1.6 seconds, which I'm pretty sure you could. Blended with the higher octaves. Kind of, yes. Yeah, so the octaves are all overlaid on top of each other. But that's not gonna stop it from, like, if there was a note played a second ago, let's say it's yellow, and now the only note that's being played is red. For 1.6 seconds, you're going to see that yellow, like, slowly disappear and turn into red. If it's in the lowest octave. So even if the other octaves move to red faster and stop having yellow output, the fact that the lowest octave is still going to have yellow output, you're still going to end up seeing colors that are no longer relevant. They might be smaller in comparison to colors that are relevant, but they're still there. How the other color chord algorithms. Oh, well. I don't know. If that's the data, that's the data. Yeah. However, if you don't keep all that extra history and you make the history the same on all the octaves, then you don't have that problem. But then the whole benefit of adapting the bin widths to the notes, like that whole benefit gets completely thrown out the window because you're gonna have way too specific bins at the top and way too wide bins at the bottom. I guess really the lesson here is, no matter how hard you try, you can't avoid the fundamental problem of the Fourier transform. Which is always a trade-off of temporal resolution to frequency resolution. Damn it. Almost like we can't do anything about that. Okay, where is the... Oh, God, I hate reading this code. Yep. Where is this stupid thing? Note finder. Do progressive DFT, I think that's the one. Alright, here we go, that's what I was looking for. Which is the one that they use as default now? What is it? Example configs? Radio? That's why wavelets are somewhere optimal in that field, but not great for binning on Western scale. Yeah, I'm not gonna claim to understand how I could apply wavelets to this problem. There's probably a way to do it, but something tells me it's gonna be a hell of a lot less optimal than this, like processing time wise. Okay, 0. So they use do DFT quick, which fuck if I know where that comes from. This is what I hate so much about C code. Total guess as to which one of these it is. Okay, luckily there's only one, so I'm just gonna assume it's this one. Okay. Wow, that's short. Huh. Okay, for every bin... Oh, does this not even resample then? Oh, this just straight up crunches through all the bins. Okay. That's one way to do it. It doesn't allow... Yeah, but if you have the same function defined in 2 places and you only include one of those files, that's super hard to figure out at a glance which one's in use. Depends on your compiler arguments, and or any includes, and or any headers, and or a gazillion other things. Do DFT progressive resamples. Okay, but the one that you now choose as default is do DFT quick, which I guess doesn't resample? Huh. Forgot about the whole one header file library there. Okay. Oh, wow, this is like, we're using floats and sines and cosines directly. Oh my god! Did you call this DFT quick? I mean. AVX file. Yeah, this is... I can tell you for sure this is not getting optimized. These people compile with TCC. Okay, so... I guess, yeah, this just calculates every bin. There are effectively no optimizations whatsoever. It's literally like code in, assembly out, done. Or not assembly out, but you know what I mean. Frequencies, quantities, oh, sine and cosine. Skip is not sure what that means. FTQ. Is it? I cannot understand this. This skip is really confusing me. And then also, what samples is this running on? Skip. Does this, instead of resampling, just use, like, instead of adding 2 to the n samples for each lower octave, does it just look at one sample? Because that's kind of what I'm reading right now. And I might be wrong, but if so, uh-oh. That's a yikes for me. It's, what? It's doing circular convolution, which is mathematically correct. Can I get that in, like, words that Dum Dum can understand? It loops back around and looks really weird, but it has all the nice math properties of the it loops back around. What's looping here? Acting like a ring buffer. Oh, are you saying that as it only takes one sample out of the buffer instead of, like, let's say for an octave 3 down, instead of taking 16 samples and summing them together, averaging them together, and using that as the sample. It only takes one of the samples, but with each iteration, that one is shifted forward by one. So you end up doing all 16 just over 16 cycles. Is that what you mean? Oh. And that works? You can do that? What? I don't really like it. It's not how I would code it. I am amazed that that actually works properly. I don't see how... Huh. That's bizarre. At one point I did the math and I think it worked out. Okay. I mean, it clearly works to some extent, because it works in color chord. Huh. So instead of resampling, you just take different micro samples. Okay. Anyways, I'm not gonna do that because I don't understand how that functions, but alright. My other question, I assume you weren't here when I asked this, do all of these use IIRs? Or are any of these like a proper, like, shift register style FIR filter? That's a lot of question marks. So at the very least, the one that I implemented in colorchord.net, which I think is like the do progressive skippy, it just gets the newest magnitudes, adds them to each of their bins, and then IIRs the bins down a bit. This data is not kept. You don't then subtract this same quantity later from the bin. The bin only ever gets added to and shrunk a little bit as an IIR filter. Versus what I plan to implement is you add a quantity and then a window size later, you remove that quantity. If that makes sense. So instead of an IIR, it's a big old shift register for the samples that when it enters the shift register, it gets added to the bin, and when it exits the shift register, it gets removed from the bin. Okay, damn it. Because the dilemma that I've been stuck here considering for like the past hour is if I resample down across like, let's say 8 octaves, that very last octave is gonna have I have two choices. I either make that octave's window size the same as all the others, and therefore have the same amount of audio, or sorry, no. I resample down and keep that set amount of audio data. So if there's 0.5 seconds of audio data in the top octaves buffer, there's 0.5 seconds of audio data in the bottom octaves buffer, and therefore the buffer is much shorter because it's been resampled, which completely destroys all of this like bin width optimization I've been doing, because well, the sample window is now 1/128th the size, so all the numbers are completely off. On the other hand, I could keep the window size the same across all octaves and therefore have more audio data, have twice as much audio data in each lower octave as the higher one, which would allow me to keep all these nice properties that I've been working on all day of, like, you know, bin widths and overlap and all this, at the cost of the lowest octave having 128 times more historical data than the top octave does. And I don't know what to do. How much work is it to just try it? I mean, what do you mean just try it? I know the result either way. And I was calculating earlier, if I go for, if I want to span if I want to span 8 octaves, and I have a sample rate of 48 kilohertz, which is the default on my system at least, and I want to have frequencies going from 22.5 hertz all the way up to 5,760 hertz, which seems like a pretty good span for music to me, 22.5 to 5760. That means that at the top octave, I've got 12.6 milliseconds of audio data, and in the bottom octave, I've got 1.6 seconds of audio data. I guess I don't have a good read on how long a really low bass note typically lasts for in a piece of music. Yeah, that's fair. And you can look at some music. What do we want to look at? Let's do the stream intro music. Yeah, 1.6 does seem long. So then I was like, okay, I don't have to go all the way down to 22.5. That's pretty low. Maybe I'll stick with 55, chop out an octave, and that halves this. And that's only 0.8 seconds, which still feels long, but for bass notes, it's probably okay, maybe? Settings are the same. Oh, this is like total garbage. Hang on here. have this all configured on my account, but I'm not using my account here. Alright. Oh, this is linear. That's another problem. Oh, okay. So yeah, if we... Granted, it's not like Audition can do any better, so it's gonna be kind of blurred here too, isn't it? Oops. Alright, so... Oh, this is gonna be like super loud. Let's take this whole thing down by like that. Okay. And then, yeah, the other thing I was like, okay, bass notes typically are longer. Like, yeah, 0.8 seconds wouldn't be bad on this song as an example. Then I was like, you know, if I want to do beat detection, though, I'm going to need way more resolution than that. But then I thought, okay, I can probably just do beat detection out of band. Like, do a whole separate thing for it instead of trying to pull it out of this data. In which case, 0.8 seconds is probably usable. Maybe? Let me specifically play only this. Yeah, I mean, 0.8 second. This is just one random example of a song, so don't take this as a representative sample, but 0.8 seconds is definitely workable on this example. What's a song with a more interesting bass line? Yeah. This one seems okay. What does this one like? Oh, this one barely even gets down there. Okay, that's not a good example then. But this one. There we go, this one does it. Okay, I don't even need to play this. I can see very clearly that yes, it would be fine. Okay. I don't know. Picking from random songs and trying to analyze them is not the way to do this, though. 0.8 seconds. In a 120 BPM song, every beat is half a second long. So the history on the lowest notes would be approximately a half note. Most bass lines are probably slow enough where that's okay. And, you know, worst case, you just chop out an extra octave and boom, you've cut it down to only 0.4 seconds, right? It just feels kind of... It feels like it's going to get out of hand if you just even add 1 or 2 more octaves. Curious what this part sounds like. If we chop out the actual part here. Yeah, these are all long. Yeah, okay. You know what? I think I'm gonna go for it. I think it will be okay. And you know that's the thing though. Worst case, like I said, you chop out an extra octave, you don't get some of the higher instruments, but suddenly it's twice as good. Just don't crank the octave count up to like 12 and you should be okay. Adding a toggle to switch between FIR and IIR mode also is feasible. Probably wouldn't be too difficult. Actually, that would probably be pretty simple. So you can put it in FIR mode to get... No, because I would have to change the size of the arrays. Never mind, that wouldn't be as easy as I thought. Okay, I'm just going to start by implementing it the way that I've been planning all along, which is to have the nice bin widths across all octaves and have the lower octaves contain more historical data. I think that'll work. However, I think it might be getting a bit late today for that. I'm pretty happy with the amount I've been able to get done. So I think I might call it here. But I'm going to commit all these Matlab simulations and everything up onto the repository in a moment here. So if you want to play with it yourself, you can be my guest. Go nuts. Let me know any interesting findings you come up with. But I think I'm going to call it here. I'm going to wait until you get the bugs worked out for trying to get into OGCC. Yeah. Let me do all the hard work and then you just copy paste the code and turn it into valid C syntax and call it a day. You've helped me enough with the Matlab stuff. I'm not upset about that. Yeah, okay. I think that's gonna be it for today then. This was fun. It's been a while since I've streamed development, and I've forgotten just how much I missed it. Yeah, you as well. Good night. Thanks for joining in. If you're still around, Get Noob, thanks for stopping by as well. I know Isaac has already left. And yeah, I'll probably do this again in a couple of weeks. Maybe by then I'll have this implemented and we can chase down bugs together. Woohoo. Alright. See you around.